Alright, so I am not happy with how long of a break I took. But one of the things with psychology, I think, is even if you take like a really long break and you're like, man, I just wasted 3 hours of time, and now I'm a little bit tired. Don't let that. It's like a. It's like a. It's kind of a sunk cost fallacy of, man, I wasted a whole bunch of time. Let's just stop working for the entire day until we go back to sleep. But we're not going to do that. We're going to say, fuck it, I wasted some time. That sucks. Let's just drink some more caffeine because we still got a little bit in us. We're not in our freshest state. But let's just hack out some code and keep on going. So that's what we're going to do. We're going to be like, fuck it, yeah, I'm a little bit tired. But fuck it, we're going to get going here. Let me open up Torch browser and look at my chat logs. So that if any of you happen to be messaging me in the chat, I will be able to see it. So let's hold on here for a second. I'm loading up my dashboard right now. My stream manager, I believe is what it's called. Yeah, nobody watching. I didn't expect that to be the case. Maybe I should get one of those little countdown thingies, right? So we are on part 77. And I guess that makes it PAINT5D part 10. And this sucks. 10 parts on this sprint so far, then there's going to be more. So, done. And let's get going here. So, we have these put functions. So put brush state, it was pretty simple, right? It's just like, we got all these different things that we need that are in the signature for the PAINT5D put function, right? There's a function just called PAINT5D put, and it doesn't use a brush to put the value. It just no, it doesn't use a brush to put the value, and to put the value on the into memory. This does not actually put a value into memory. This function here puts the value into the brush, but the brush has all the same location information as the put command. The command that's just named put like this. It has all the same exact parameter names in the exact same order, and that is by design. Tile value being the last parameter because it is the parameter order of the function AAC 2020 PAINT5D put, and we have a little timestamp from the previous video right before we ended that video, actually, that goes over that. So we don't need to go over this too much. The main thing that we're really concerned about here is making sure that there's no integer overflow, right? That the values are actually in the range that they should be in, and that we set the values in the correct location. So it's in tau 15 in the PAINT5D subsection, and we just got to make sure these things match. TQ, TE, TL, LX for local X, LY, local Y, AD for offset dex, or offset index, and TV for tile values. So that's all the things that need to be set for this to work, and it says finish this function. Nope, we don't got to finish this function. We are done, but we could add a return. And this thing should return void. Good. Now, the last thing we want to do is put using brush. So put using brush is pretty simple. All we're going to do is do almost the inverse of this. We want to get all the brush state and then use that brush state to put a value, right? And the value, we're not going to toggle a value. We're actually just going to, whatever we need to get, we're just going to get it, and then we're going to put it. So let's copy all this, and let's just paste it in here. Remember, this is going to be a get, so get all brush state. So we could do get like this, all brush state, and then over here we could do a get all brush state like that, and that way we could write this similarly with a put colon and a put colon, and the reason for that is now when I highlight this, I see all brush state, and then I see this similarly named function that's a get. So I can see the relationships between the two pieces of code pretty easily. Now, because we're in the get section, we want to name all these get. Also, by design, we have made it so that the signature for the get and puts have everything in the exact same order. But the difference between the getter and the putter is that the last 4 parameters, instead of being values, are actually pointers to the values. Because they are output parameters, so we have to return them in such a manner. So we will keep everything kind of similar, but we'll wrap things. So we're going to wrap everything like this. And for these unused values, they also need to be wrapped as well. So to expedite this process, we're going to kind of, right, we're not using Emacs or anything, so we're going to do this in a very systematic order like that. Let's line everything up nicely. And now, what we really want to do is, yeah, the casing just sucks here. The fact that I have to, well, let's just bite the bullet and kind of painstakingly do this. Let's put some X's here to make absolutely sure we don't mess this up. We're just gonna do the grunt work of kind of pasting this in here. Let's not try to save time by figuring out the fastest way to do it, because by the time we figure out the fastest way to do this, we'll have already done it the slow way, unfortunately. This is just one of those things that sometimes there's a lot of monotonous work. You don't want to do monotonous work, but at the same time, sometimes monotonous work will find you, especially with code. At least we're not like 1960s programmers, because they had a lot more monotonous work than we do. So be glad that we have, you know, the technology that we have, and that though the code may sometimes get monotonous, it'll never be as monotonous as what 1960s programmers have to put up with. So we have these things here. We have these variables. Now, we need to declare let's do dec declare brush state variables. All right, let's call it declare brush state variables. We don't have to get too fancy with what that name should be. And in here, what we're going to do is all these things, the TX, the TQ, etc., we're going to just copy those and paste those. So CS start right now. And oh yeah, also, you know, no, seriously, ask me anything. Seriously, ask me anything. Okay, so now that we're here, let's take TQ, put it on our clipboard stack, wait a little bit, put this on our clipboard stack, wait a little bit, put this on our clipboard stack. And the reason I have to wait is because my clipboard code isn't the most well written. And if we try to Control-C too quickly, the code doesn't execute in time, and we end up losing things on our stack, which kind of sucks, but that's the way it is. So we still save time by waiting a little bit. God damn it, no. Oh, no, it's not CS paste, it's CS dump, right? CS dump. There we go. Okay, so we got these values. They need to be U32 values, and the reason for that is because they're getting values that are encoded in a pixel. And the pixels are 32 bits because 4 bytes makes 32 bits. 4 bytes being RGBA color. These unused values are unused pixels because we store everything in a cluster of 4 pixels, and if we don't need certain values, then we just don't use them, right? So with that, so we have put using brush, and also we could expand these later if we ever find a reason for like what to use with here, right? So maybe eventually we want to encode like the previous value, and then we can get some nice transitions, and I think that'd be pretty cool. So so we have the possibility to add that kind of feature, so I'm kind of psyched about that. But yeah, so this is, you know, it's a 32-bit, so it's unsigned, so 0x. We could just, for a trap value, we could just go, I don't know, 1 dash 10 100. How about that? Yeah, like something like this. I'm just thinking of some like kind of weird pattern that I can, when I see it in the code, I'll be like, I'm pretty sure I put that pattern there. Pretty sure that's not what it should be. Pretty sure we forgot to initialize that, right? So let's kind of put this in here like that. Okay, so that's going to be their initial values, and they're all trap values, so we should probably say, like, trap value. And a trap value actually has a definition in our hashtag file, so we'll put a little @ symbol by it as well to be like, hey, you can probably look this up and figure out what it is. Okay. So, you know, even though we could do that, I think the best use of our time for this value, I think it would be better if we did like trap val, like that. And make sure it's in the documentation. I think we have a shorthand version of trap value, so let's see if we do, yeah. Oh, no, we don't. We have kind of this thing. Let's just put a note here. At trap val. At trp val. Shorthands of trap value to save space. Right, to save column space, that's what we're talking about when we say save space. But yeah, now we definitely have it in our little documentation thing. And I think I just want to use trp val like that. Trap value. Or maybe at trap value like that, because really, we're talking about, when we want to abbreviate things, usually we don't want to do it this way. We want to take just the first 3 letters and keep it simple. So let's kind of abide by that and kind of stick to this one. And then go here. So trap, right, now it's kind of more cryptic here, but the idea is, I want to put the longer variable names in here as well. And I thought maybe I could get some room for that if I kind of, you know. It looks to me like we're not going to have room, though, if we insist on putting these little trap values in here. So maybe, if we're lucky, well, we could just do at trap, and then, let's just do that as well. Okay, right, so we just added some more things for the trap value. At vid IID 0077, and the time is 0 hours 13 minutes and 35 seconds. And so right here in this video, we just want to explain that we've added these extra at trap value things so that we can write them more shorthand, right, and take up less column space than writing them this way or that way. Because sometimes we're kind of limited on column space, and we got to write things a little bit more succinctly. So tile quadrant, this is the tile exponent, which determines the size of the tile, the layer that the tile is on, the local x and local y. So this is going to be something like loc, and I believe it's going to do tx and ty, I believe, if I'm correct. We can just look for this in another place and make sure. Yeah, max loc x, yeah, so that's correct. I just want to make sure. The offset dex is like this, and the tile value is like that. Awesome, so we got like all the variables we need. Actually, we need 2 more. We need a U32, a U1, and this is unused number 1. And then we have 2 more of those. So we have 2 and 3, so unused 2 and 3 as well. This is just a oddity of how I designed the API. I decided every variable gets 4 pixels on that texture regardless if I use them or not. And the reason for that is just to keep the data as homogeneous as possible, and it does waste a lot of space, not too much space, but it also gives us room to expand the system without any dirty hacks, right? We have these like 3 extra possible variables here that we could use to expand how we do things, right? And we could actually use these extra values to do some animations between previous and current values. And that would be pretty nice, right? Because we get those smooth transitions. So TQ, TE, this is TE, yep, TL, LX, LY, AD, TV. Okay, so all these match. So the next part is making sure that these values are in the correct range, right? So we want to range check these before we set the value, even though the setter for these values also has range checks. But it would be good to range check it here as well. Just, it gives us a little extra redundancy in the code. And also, if the range check fails, it'll fail in this function rather than in a function further away from the source of the problem. So extra range checks I don't have a problem with. It's a very defensive type of coding that I do. But let's do it. So range check extracted variables. So we're going to range check the extracted variables. That's a pretty accurate name of what we're doing. It's kind of a little bit fancy, like it almost sounds like we're trying to be a little bit smarter than we actually are. But I mean the words mean what they mean. It's not a... We're using big words, but you know we're also programmers, so maybe we're allowed to use big words. But actually I am against big words. The word should be no more complicated than what you need to describe what's going on. If it's any more complicated, you're just adding noise and confusion and using a word that less people are going to understand, right? So you want the least common denominator in your code as far as I'm concerned. As long as that least common denominator is you know, accurate enough or precise. I always get those confused. I know one means the ability to replicate a result, while the other one means the ability to get close to the actual real result that you're aiming for, but I always forget it. So, yeah, so let's actually range check these, and we already have some range checking code, because we already did these crazy, ridiculous range checks right here. So, what I think I might want to do is say, this is a bounds check. Let's do this. Bounds check, and let's call this one inputs. There's a reason for this, right? Because we see the similarity in the code, so why don't we not bounds check inputs? And why don't we do, I don't know, TTTLLAT, right? Because that's the it's a little bit weird, right? But the idea is that that it's the first letter of each one of these variables. Or actually, how about this? 7 vars bounds check. So the idea is I'm trying to make something unique enough here that it's bounds check is a little bit generic. And so if we say 7 vars, 7 brush vars bounds check. Yeah, let's do that. So I just want it kind of more unique than it is right now, this section. So here's what we can do. Now that we have these 7 brush bars bounds checks, we can take this code right here. And in this other section, where we just extracted those values, instead of say range check extracted values, I mean, we could put that there as well, right? But then we can take this brush vars bounds check thing, so we can kind of double label this, but instead of inputs, it's going to be outputs, right? So we have some symmetry between those code sections. In fact, I so much like the symmetry between the code sections that I'm going to take off this label. We could also, you know, make an extra label here where we can say it in here like this. Range check extracted variables. If we want a little bit of extra stuff. But the idea is now I can kind of highlight this, and these are the brush variables, right? And then over here, we can go up here and we can see that same exact section name. So it helps maintain these connections between analogous sections of code. So the max values, right, we're going to be able to assert these ranges easily. Because remember, we're getting a pixel value, and the pixel value is in a U32. However, greater than or equal to 0, that check is always going to pass, right? Because it's it is what do you call it? That value is, it's unsigned, right? So it's never negative. But I think that hold on. Where do we want to put this? Do we want to, like, put it in here like this, and then move this over here like this? Yeah, I kind of like it like that. So we're going to do some casting craziness to allow this comparison, even though it's kind of pointless. And the reason why is because what if the types change? What if we end up using different types later? I want to be able to... make this comparison, even if it's a different... Even if this... right, even though it is... These types could change in the future, right? They could change to signed types eventually for some reason, as far as I'm concerned. And we don't want to allow that to get in our way, right? So, now we're kind of still in a little bit of trouble here, where we have this ridiculousness here, and it's taken up a lot of room. Just a little bit too much room as far as I'm concerned, but you know what? I mean, why are we doing this? If we really want something shorthand like this, why not just A for assert, right? A for assert, and now you got enough room, right? And it's not like you have to remember this forever. You just have to remember in this scope, and since everything's kind of very repetitive here, right, it's not a problem. Because you know this is an assert block, and that inside here are all the statements that you are asserting, so it's not a problem. Okay, so I like that. Now the next thing we want to do is we want to check for overflows. Overflows is a little bit redundant, but like I said, I'm not going to... I don't care. So check for integer overflow. So are these the inputs still? Yeah, these are still the inputs. So let's call this inputs. How about 7 brush vars int overflow chk, right? So we're abbreviating it a little bit, but 7 vars int overflow chk. It reads well enough to me, so I can look at that and I can know what that means. And the reason why we're doing this, once again, is because then we can take this name, it's a little bit more unique, and then we can go into the section down here, and we can do the integer overflow checks. Okay, and unlike the other integer overflow check, we're actually going to use these because we need a we need versions of these that are U32. So what we could actually do is we could use all of these variables, but just make, did I say U32? We need a U08 version of these. So we could take all these variables that we already have, and we could make the U32 versions, right? So we could take all this, and we could actually probably swap the places here. So we could just go bam, swap the places, put this one in here. And so now we can see the connections between these, right? Because we can highlight this, and we can highlight these, and we can see it all. and everything is kind of still lined up, so that's nice. But instead of this being U32 right here, this is the U08, right? So we need, so this is, so why do we have these U08 values? Put using brush. It should be because if we look at the PAINT5D notes, up at the very top, our put function, yeah, it takes U08 values. Even though internally it's going to have to, like, change those back to U32. So there's a little bit of, like, ridiculousness here in terms of casting more than we have to. And that could be a possible point of optimization where eventually we say, stop all this crazy casting and use exactly the types that we need to have at that point in time. But for now, we're not going to... change that. Okay, I almost broke my file there. Okay, so I mean it's a notes file. It doesn't matter if we, well, just because it's a note file and it's not going to be compiled doesn't mean that we don't want to, you know, that doesn't mean we want to just delete random sections of it. So we got to be careful there. Okay, so U08 values to use with so right, so we could say U08 values used with. Yeah, I like that. It fits. And it says U08, so it's not too hard to know exactly what that's for. And U32 values used with. And these are used with the tau depot get, right? So these are all tau depot get functions, so we can just say, you know, tau depot get, and we're done, right? So if we look at this, that all lines up nicely. I'm happy with that. So we have a getter. We have the get values that are U32, and then we put values that are U08. And in the interim, we do bounds checking on them. So now that we're kind of like doing this right here, int overflow check can also do the assignments as well. So we can take these, and we can say that let's make more room. You can just say that, you know, these guys equal U08 cast of these guys, right? Right, so equals a U08 cast of these. And the next thing we can do is say, okay, well, we casted these, but we're expecting not to lose any information. So if that... overflow check. This is overflow check and assignment. Right, we're doing overflow check and assignment here. Also, when we did this brush vars thing, didn't we say that, yeah, inputs, and now we have outputs. So we're gonna, so right here should be called outputs, right? So we have these sections that are all tagged with outputs here. Get all brush state, so a little bit different at the top, but yeah, we actually want to label these as here's what we're doing, but it applies to the outputs this time instead of the inputs like in the previous function above. So that looks good. Does this match? That matches. Awesome. So we just want to assert that that if we did, so the way we're going to do this now is we're going to do till qua equals, and then we'll do a U32 cast of TQ, right? U32 cast of TQ like this. Okay. So we just want to do these asserts. It's important we get these asserts correct and don't do a single equal, because if you ever had the it works in debug mode, but doesn't work in release. Well, actually, or this would probably be, if we did this, it'd probably be more of a case of it doesn't work in debug mode, but it works in release. Yeah, we don't want to do any accidental assignments inside those assert statements. So anyways, 1, 2, 3, 4, 5, 6, 7, right? Copy that 7 times, and then we just got to paste and paste and wait a second. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. Okay, so I just pasted the wrong amount of times. So obviously we don't want to have to count these every single time we're looking at the code, and that's what these checksums here are for, right? So we can take these checksums and just be like, all right, there's my checksum of 7 things. Let's make absolutely sure that there are actually 7 things over here, right? So we can just move this checksum here, and then we can move another checksum over here, and there, bam, 7 things. Right, so we're going to assign them, then we're going to do our asserts, and then after all of that craziness of, getting all that brush state, then we can finally use that put command, right? So, call core command. I'm just going to call it call core command put. And the reason why is just if I want to make a section that is called call core command get, I can do that. And I bet that if we look up at the code, the other section up here, I bet there's an analogous thing or calling a get somewhere. So put brush state, actually no, because it's the brush stuff. It's not, yeah, it's not the brush, it's the brush stuff, it's not the, yeah, we're fine here. So put brush state, but we can still keep it called call core command put, right? Because it's one of the main functions of you know, main data interface put. And I think, do we actually tag something like that in here? No, we didn't. We just tagged it here like that. Sure, whatever. Let's kind of double label it like that, because I do like calling it main data interface. I think that that is somewhat descriptive of kind of what we're doing. Okay, so now that we have this doubled section here, where we double labeled it, let's just call that put command, and we actually have all the variables correctly named for calling it, right? They're already all there, right? So tilqua, etc. We really need a shorter hand. Oh, actually, once you get rid of the sign, the type, then that problem actually goes away, so never mind. So yeah, we just call the put command. The put command returns a UO8, but we're not actually going to use that for anything. Tile quad, tile exponent, tile layer, all this stuff. It's all there. It's all accounted for. Now, do we really need all this explanation over and over again? I don't know if we do. However, we could, if we really want a checksum, we could probably throw one in over here. Like this, you know, 01. Actually, no, there's only 7 things, so we don't need 2 digits. We can just go like this, right? 2, 3, 4, 5, 6, and 7, right? So we are sure that there are 7 things there. If we really want to be compact about it, we might be able to get away with just indenting it a little bit more properly. I don't know. Yeah, that's still a little bit of a God damn it. Hold on. So I tore my bicep a few months ago, and sometimes my finger just gives out. Okay. Ah, fuck. God, this fucking sucks. I hope I get this back, because sometimes my finger just spazzes out, and I can't... God fucking damn it. Yeah, the nerves in my finger just spaz out, and I don't have control over them, and it fucking sucks. Okay, so let's try not to be too depressed about our body that seems to be failing us. And yeah, let's just write it like that, right? We got a little checksum, and we're using the put function. Okay, that's all we need. And then for this, we're just going to return, right? And we're just going to return. We're not even going to return anything. I don't care. It's just, you know, we have this put using brush command. The next thing we want to do is, well, we have a U32 and UO8 everywhere, I believe. I don't think we have any other types besides those 2 types. Oh, int32. Okay, so let's define U32. Then define int32, and then also UO8. Define UO8. And with these types defined, we have everything that we're working with here. We can do a little checksum here and say, hey, make sure that you got 3, right? So little checksum right here at the top. And then at the bottom, we can look at this section label here, and it should be only in 2 places. Excellent. And we can paste this down here. We can change this to undef, and then we can add a space, and then we can delete all of this junk in the middle, because we can't have stray tokens at the end of our undefs. That looks good to me. Now the next thing is, where are you being called from? You should be being called in a unit test. And the naming should be regular enough that if I select put using brush, we're going to find the unit test functions. And there they are. Put using brush and put brush state. So let's also select the put brush state and make sure that that goes back to the function that we're calling. And we can see put brush state right here. The actual function, why is this function being called already? Oh yeah, because we need this function in one of our tests. And we thought we were done writing tests, and then we're like, man, we need this kind of helper-ish type function. So now we're going to have to create another function and create tests for it, and this sucks. And that is why that's also already used in a place. So the thing is, if we're going to write these, if we're going to use these new functions somewhere, then that means we have to test them, right? So put brush state and put using brush. So how are we going to test put brush state? So, well, simply, all we should have to do is, well, first of all, let's think. We got 7 different variables. So this table could get kind of big. So let's do like int32 and we'll say well, actually, all these values are unsigned 8-bit integers, so let's just use UO8 and table of unit test code. Okay, and the table of unit test code is it's really rows times calls, if you really think about it. So we'll name it this way. I know I've been naming it different ways all over the place. But then over here we can do define rows, and we'll have at least 3 tests, right? So these are a number of tests, and define calls, and the calls is 7, or actually is it 7 or is it more? Num elements in one test, right? That's what that is. And then over here, before we get out of this test, we should probably, you know, undefine what these macros are. We don't want to leave any stray macros in the program, and hopefully we haven't. But if we have, oh well, I don't know what to say. We'll find out by some angry user of our library that's like, hey, you leave these stray macros, and I wanted to use this variable name, but I can't because I used your library. That would be a bad situation, right? So rows and columns. Rows times columns equals everything we need. We're saying there's going to be 3 test cases, and what do we have here? We have like a, let's just try to be very compact here, because 1, 2, 3, 4, 5, 6, 7. We know we need at least this, because this is going to be for putting the brush state, and we're going to use the shorthand versions of the function names, the function parameters over here. We're going to use the shorthand versions, and we're going to label them in a comment right above where we're filling out this table, right? So we're going to say like this right here. This is going to be TQ for tile quad, and this is going to be TE for tile exponent. This is going to be TL for tile layer. This is going to be LX for local X. This is going to be LY for local Y, and we did LX, LY, and not TX, TY, right? I'm fairly certain. It's like maybe we should have done it a different way, but I believe that's kind of like how we did it in our code, isn't it? Is it not? Let's look at push brush state for a second and see if that's... Yeah, so we used LX, LY instead of T's. which kind of helps break up these t whatevers and these, right? I think it helps break it up, so we're going to stick to it because that's the way we've done it with the other code. So we want to be as consistent as possible. So, you know, that's what we'll do. So, okay, so LX, LY, and then OSDEX, and finally the tile value. So that's the order that we've been sticking to, and thus that will be the order that we fill things out in the test table. So what are we really expecting here? Well, we're just expecting that whatever we put ends up being what we get. So there's only one spot for all this stuff, right? Because we're putting the brush state, there's only one brush. So we can do puts then gets interlaced like that without any problem, because there's only one brush. There's no potential to be storing data in overlapping locations, because there's only one location. So by the nature of only being one location, the location always overlaps when we set data, right? It's always an overwrite if we set the brush state again. Okay, so with this, setting everything to 0 is actually a decent first test. And then the next test we might want to do is use all the maximum values. So if we look at PAINT5D, we should have kind of a table of maximum values here. So we see there's a 3, the tile exponent maximum is 7, the tile layer maximum is 2, and the LXLY is actually dependent on that exponent value, right? So if we use the largest exponent, so the tile exponent 7, there's only one place we can be, right? There's only one place we can be, so we'll have to do that. The offset dex, the maximum offset dex is 15, so we could stick with that. And the maximum tile value is 3, so we could stick with that. And that's a nice little thing here, so let's just keep on going with that and use... let's go move down on these tile exponents, right? And so if the tile exponent is 6, then instead of the maximum local x, local y being just one cell, it's a 4x4. So this is the maximum kitty corner place we can kind of be. And we could kind of do that with every single one of these. So 6, we could do 5. And so if it's 5, instead of having a 2x2, we're in a 8x8. So that means that these maximums should be able to be 7s. Okay. Okay, so let's go down one more, and then instead of being an 8x8, we're in a 16x16, so these maximums are going to be 15. And let's do this one more time. So 5, we're going to do it all the way down to the bottom. So 3. So 30s and 32s and 32s makes 31s and 31s. Then we'll do, this is 2 for the tile exponent. That means the maximums are 63 and 63, right? Because it's 64 minus 1. And then, right, the reason why we're using the maximums is we're trying to hit all those edge cases, right? So 64 times 2 is 128, so that's 127 for this maximum. And this maximum, right, we're going to do the maximums on both. And then 0. 0 is the smallest tile exponent, and when we have that, we're inside of a 256 by 256 area. Now, I'm not sure if that seems right, so let's make absolutely sure that's right. And also, it's not 256, it's 255. Okay. Let's make sure that's right. So if we look at our diagram in PAINT5D, data should have a diagram, and we see that that's not correct. We're off by something here. Because the smallest tile exponent 0, is actually giving us a 128 by 128 section here. So somewhere we have screwed up, we've missed something. And if we look at this, we got the 1, 2, and we're missing, for the sizes here, 1, 2, the 4, right? We're missing the 4, right? So if we move this over, paste this here, we're going to see this is 1, right? We're going to add 1 to each one of these values. 1, 2, so the 4. Where's the 4? Here's the 4, which is a 3. Kind of confusing. Now, to make it easier, what we could do is, since it kind of makes sense to be able to express these as as it would make sense for us to be able to express these as values that are like powers of 2, rather than these powers of 2 minus 1, which are really confusing to look at. 7, 6, 5, 4, 3, 2, 1, 0, right? Powers of 2 minus 1, that's kind of confusing, but if we start doing that for everything, then, you know, technically this is 16 minus 1, right? Technically this is 4 minus 1, right? We could, right, this is 3 minus 1, right? This, I guess, technically it doesn't change. The tile quadrant doesn't really change, but it's 0 indexed. If we want to do 1 indexed and then minus 1, right? So everything starts to, it could spiral out of control really fast, and we don't have much room. So we're just going to keep it like this. And now these are the maximum values for these. Let's create a little checksum here. So we have, let's move this over here, because we're going to duplicate these 2 more times. So let's do, let's say, can we do like a, can we do a local checksum maybe? I don't know if we can. We don't have that much room. Okay, we don't have that much room. We're not going to do that. So we know that this is. We're going to go with this. We're going to go with indices rather than a checksum, because we're going to have to look at these test indexes later. So 01, 02, 03, 04, 05, 06, 07, 08. And now that we have these, we need to just paste them and say, okay, so we'll just say using maximum values for all fields, even the local XY board, LX, LY. So that's what this is. That's what this series of tests is. And what we could do is, we have this little table here, right? We can take this table and we can kind of paste it below here so that we can see, oh, hey, this is what we're talking about, right? And this looks kind of bad. This is aligned, but then it's like, it's no longer aligned here. Oh, I see. We're aligned to, we're right justified. That's fine. That's fine to be right justified. So we'll take what we have here, and we'll just be like, copy it, and we'll paste it, and we want to make sure we don't have transposition errors. So the way we'll do that is we'll just, there's no way to check for transposition errors here, because the only value we can use is 0. But for over here, what we could do is we could just blank these out, 0x0, so it's kind of obvious. Check previous test, but all local x's, LX, are 0 to detect transposition errors, right? So we're just taking everything and we're being like, hey, all the local x's are going to be 0 to check for transposition errors. Then we're going to take this again, and guess what we're going to do? We're going to take this same commentary, but we're going to change it to ly. So same commentary, but local y's, and then ly, right? So ly versus lx, and then we actually have to do it. So right here, we're going to say, like, 0x0. And let's actually make this one 0x0 as well, because, right, so, it is kind of weird to have hexadecimal 0 and then just a decimal 0, but the idea is that we can see the analogousness or the complementariness of this block and this block here, okay? So now these checksums, right, so this is 0, and then we go up to 8. And so let's just name these, right? So, 9, and then this is 10, and then everything is off here, isn't it? So I don't know how we want to do this. I guess let's just do this. 11, 12, 13, 14, 15, 16. Does that make sense? 8 and 8 is 16. Oh, god damn it. We put that checksum in the wrong place. So let's try to shift things around here really quick to get things back to where they need to be. And I'm being stupid. That's because I probably am slightly fatigued. The caffeine makes me not realize it. So, okay, so we got 0, and then 1, 2, 3, 4, 5, 6, 7, 8. So this, 8 plus 8 is 16, and we're adding another 8, so that actually does make sense. I was expecting it to be off by 1, not exactly 16, but that makes sense because there's already 8. We're going to add 8 more, get 16. Okay, so now that means this should be up to 24, right? So, so 17, 18, 19, and this is going to be 20, 21, 22, 23, and 24. Okay, so that's what I expected, right? I know those values, 8, 16, and 24 pretty well, because RGBA byte packing, right? So that's why I know that. I don't know my multiplication tables very well, unless they're somehow related to the math you need to do for bit packing. So for these maximum values, yeah, I mean, that's good. That's good. Yeah, everything looks good here. Now that we have this table kind of filled out, we need to go, hey, there's a 24 and there's a 0. That means there's 25 tests. So the number of rows, the number of tests, right now that's 25. And we don't want to screw this up. Too low won't cause a problem in the code. But if we go too high, that'll segfault, so we wouldn't be able to detect the problem. We just get like false positives on our tests. So we do want to make sure that these numbers are correct. So the number of rows is 7, right? And let's just make a note of that. Let's make sure, absolutely sure that's right. So 0, 0, 1, 0, 0, 2, 0, 0, 3, 0, 0, 4, 0, 0, 5, 0, 0, 6, 0, 0, 7, right? So I have a little checksum right up here. And then we can repeat these checksums as much as we want. If we really want to just kind of, you know, mash them in there like that. So yeah, I'm happy with that. We're absolutely sure we have 7 items for every single test, and there's 25 tests total, which we can assure ourselves because the checksum goes up to 24, but this isn't a checksum. Sorry, it's just the index labels. So we need a 24 plus 1. If we really wanted to do this, we could do a 24 plus 1, because we have, right, we have the maximum index plus 1, and that way when we highlight this 24, we can see 24 is the last. So I think that might be a better way to denote the number of tests in a way where we can see the connections between the different pieces of code. So now that we have the test table kind of going, we need to actually create the variables to iterate through this. So in here, let's say declare variables. All right, we'll have a declare variables section. Or declare iterators. We'll call it iterator vars, or loop vars might be a better way, like not as complicated. Declare iterator vars. So I feel like we're getting a little bit too fancy with saying that, where it's like iterator vars. Why you got to be so pretentious and use big words like you think you're smart or something? So let's also kind of say put in kind of like the simpler version of what we mean. You know, iterator vars as in loop variables, right? That's what we mean. Okay, so what do we have? So we have the test index. So let's just do int32 test index. Test index. Then we have int32 max index. Max index. Max test index. And we also need a 32 base. Base value, base offset to current test vals, right? So that's kind of a really long name, and here's the shorthand of what it is. Okay, so now that we have that, the next thing we need is to just extract these values. So we have all these values. We have them in a table here. So let's declare test table vars. So we'll call it test table vars. Maybe that's not the best thing to call it, because we're actually going to declare the test table outside of this block. Or actually, let's not call them test table vars. We'll call them test table members, because it's not like a member variable in the sense of object-oriented programming. But they do exist as members of these tables, right? So we'll call them that, and then we got to think, well, what are these supposed to be? Well, these values should always be UO8 values, so we got to think about this this test table, right? Oh, we made a UO8, excellent, so that means we can just do UO8, and then do TQ, or actually, let's just do XXX, because we're going to go 2, 3, 4, 5, 6, 7, and then look at our notes file. So we have a notes file, and somewhere we have the shorthand signatures. So here's our shorthand signature, so we can take these guys and be like, hey, there you are. Go over here, paste you down there. Take these as well, so take this information as well. Excellent. If we want to also keep a little checksum, we can keep a checksum. And I'm kind of sick of using trap values right now. They're not really helping me as of late, so I'm going to forego using trap values, and hopefully that doesn't like bite me in the butt later. So, also, it's really hard to make any decent trap values when you only have 0 to 255 to work with. So, declare the test table members. So we're going to say, since this is called declare, we're going to say declare like this. So we can highlight this, declare test table members, and declare iterator vars. We're also going to do the same thing for this, declare. Right, so we can just see declare, iterators, test table members. Makes it a little bit easier to navigate through. And the other thing is because we're going to have another section that is very similar to this, but instead of declare, it's going to be extract test table members and extract test table members. And there's no declaration here, right? It's just like, hey, TQ, what do you equal, right? And this is going to be equal to the equals the unit test, the table of unit test code with the base index plus the offset to the value, right? And so since we're doing everything in the correct order, no problem, right? 0 to 6, right? Because the first element has a 0 offset. There's all our stuff, right? Now, before we can do this, we need to get base address of test row. So we want the base address of the test row, right? So before we can extract those values, we need to get the base value. So we're going to describe, like, section that off and name it. And then we're just going to say, well, base equals the test index times the number of columns, right? The number of columns is the number of elements per test, right? So calls number of elements in one test, right? So that is the stride, right? This is also the stride, if you want to think of it like that. But yeah, just the test index times this, and bam, we got this base address. Now, if you haven't noticed, we need a loop, so for ti equals 0, and then ti is less than or equal to the maximum index, because we're going to use inclusive ranges all of the time. We'll probably never make an exception for that. Like, sometimes if we're being lazy, we won't do it, but usually I want all of my math to use inclusive ranges. Half-open ranges just annoy me, so I don't like to use them. So then ti plus plus. Okay. Then in here, we'll close off this loop and just say do a Visual Basic kind of thing and say next ti. The syntax for this is not Visual Basic, but Visual Basic has this thing where at the end of a loop they label it as next, so it's like loop, do some stuff, and then next at the bottom, because Visual Basic doesn't use curly braces for scope, it just uses these weird-ass labels. And if you're new to programming, it's actually really nice, because it helps you understand what goes to what. It also helps you avoid making mistakes, right? Because the braces have a little bit of redundancy, where you can't write all the closing braces for a closing brace for a for is the same thing as a closing brace for a function, is the same as a closing brace for unlabeled scope, right? So with Visual Basic you get a little redundancy because all of these scopes have these very specific labels, so you can't accidentally mix them together, and that's actually really nice. It's just very cluttered. Okay, so get base address. We got the base address. We extract these things, and after we extract them, what do we got to do? I mean, well, we have to actually set them. So we're going to say right here, we could say, how about we call this, let's do something like this. Use test table members. And we kind of made this section kind of weird because we want to, we just want to have, I don't even know how, let's, if we're going to use kind of like extra characters, we should probably, we need a way to section divide this where it's not going to be confusing as to how to align things. So we're going to do this instead of that craziness with all the colons, just because that way we can adhere to our pattern a little bit better. And also, we are not justified on the correct side here. So use test table members. There we go. So use test table members. Extract the test table members, then use the test table members. Excellent. So how are we going to use these? Well, we need to put the brush state, right? This is like the put test. Yeah, put brush state. So this is the signature of that function. And put brush state, what are the types that you use? So we have this thing here. We haven't kind of said, hey, what are you? We could put those types over here since we have room for it. But let's look at put brush state really quick and see what the signature is. Put brush state. So we're using int32s, wider than they need to be. And that's just so... yeah. Okay, so they're int32s. Interesting. So we use extract in quite a few places, but we could do int32 tile value, and then we could just make a little checksum as well. So we could do, right? So we could kind of throw some more stuff in there so we can kind of see what we're talking about. So we have these 7 things. Here's a little checksum saying here's the 7th thing. Here's the long-handed version of these variables, and they're all int32s for some strange reason, right? So in here, we used UO8s. So if we want to call this properly, we're going to have to do a cast. So let's just take this whole thing, right? Let's be like, bam, here you are. And let's make absolutely sure that we're testing put brush state. Yes, we are testing put brush state. So what we're going to do is we're just going to throw this down here, put brush state. And then the sucky thing is, if we want to get the brush state, then we're going to have to make a get brush state function, and we're going to have to test that as well. And guess what? I don't want to do that. So you know what we're going to do? We're going to hard code the getting logic for getting the brush state rather than creating a put brush state, because I just don't want to have to write more logic to test this out. So so we're going to put all these values, and they are int32s. So we're just going to say, you know, int32 and then these guys. And we have plenty of room, so I don't feel like, you know, removing these int32s. That's fine. Okay, so we've used the brush state, and then we want to check the brush state. So we want to run so we use the brush state, and then we want to... actually, let's take this whole block, and we'll say get brush state, right? So we'll call this get... why is this... Hold on. Oh, no. I just, extract test use test table members. Oh, okay, because we're not calling it brush state. Got it. So this is get table test members. This is use test table members. I don't know. Sure, we'll just call it... We'll just keep it as test table members, since that's kind of what we've been labeling everything. Then maybe we want to call this brush state instead, but this already says brush state here, so I'm like, maybe not. So, the next thing we want to do is, when we get the brush state, that's going to be U32 values, right? So, let's take these values and... just do like a U32 and call this actual. And we actually want to put these over here, right? So declare test table members, declare actual gotten values. And since we're calling them actual gotten values, a lot of times I use it as actual, but we put the things and then we get them, right? We gotta put it and then we gotta get it. So calling it get or got is fine, I think. So let's do that. So let's call it got. And we can take this checksum here. Right here, we can just take that and be like, hey, you go over here. Bam. That's where you are. We can also align this nicely, right? And say, hey, you aligned there, so we can see that, you know, right? Okay, so we got these gotten values. Let's actually kind of extract them. So, for here, we're not going to make a getter function for this. I don't want to make a get brush state function right now, because it's just a function that I would be using to... Right, I already wrote these helper functions to test some test code. I don't want to now write another helper function to test the helper function that tests the actual function that's testing the code I want to test, right? Like, this is spiraling out of control, so at some point we have to, like, say, nip this in the bud before it spirals out of control. So, let's make a note here. We are not going to create a... get brush state function to help test this code, because brush state itself was created as a helper function. God damn it, my keyboard's... Why the fuck is my keyboard moving all over the place here? Hold on. Yeah, that's annoying. I need to clean off my desk. Maybe my desk is a little bit dusty. Okay, so... Oh, it's, oh, I see. Okay, my cord is, like, fucking underneath. God fucking damn it. It's like, you know, sometimes you just cannot get comfortable. Okay, so we are not going to create a PAINT5D get brush state function to help test this code, because AAC PAINT5D put brush state itself was created as a helper function to help run unit test code. this has already spiraled enough out of control. I don't want a helper function for my helper function that helps test my unit test code for my actual function. Right? Like, we don't want a helper function for our helper function that helps test my unit test code for my actual function, right? So basically, what we really want is just the unit test and the actual function, and we already have this helper function, and then we want a helper function for that helper function. That is just ridiculous, right? So we're not going to create this extra function, right? And we're gonna denote that we're gonna give this a little timestamp of like why we made this choice, because we can see it kind of spiral out of control. It's like what do you call it? Inverse deduction? What is it called? Not inverse deduction. We don't mean you mean... Hold on. Okay, so in game theory, there's a thing called backwards deduction, and basically, you know, one function could lead to another function, which leads to another function, which leads to another function, etc., etc. We don't want that to spiral out of control, especially if these functions in this backwards deduction chain are only being used for a unit test. That's just, it's getting ridiculous. We have to nub it. We have to nub it somewhere and just say, here's a whole bunch of crazy code that doesn't go in its own function. So at vid IID 0077, and the time is 1 hour, 12 minutes, and 25 seconds. Okay, so let's read this again. We are not going to create a AAC 2020 PAINT5D get brush state function to help test this code, because AAC 2020 PAINT5D put brush state itself was created as a helper function to help run unit test code. This has already spiraled enough out of control. I don't want a helper function for my helper function that helps test my unit test code for my actual function. Hashtag at backwards deduction out of control. So let's actually look at backwards deduction. Let's look up what I mean by backwards deduction and see if I'm using the right terminology. So backwards deduction. So I see somebody popped on in here, so I don't know who you are. I don't even know if you're a bot or not, but you can ask me anything. And here are my demo reels. Demos. So these are my technical demos. Nice fancy sparkly stuff for you. If you want to check that out, I'm creating an engine that's a 2.5D fractal autotile engine. That's a mouthful. If you don't know what autotiling is, then that'll be confusing. If you don't know what fractal is, that's also confusing. So the best I can say is 3D graphics are not... you don't say take 2D graphics and just... 3D graphics and 2D graphics can keep on evolving and getting better on their own. It's not like to get better than 2D, you have to go 3D. You can actually keep on improving 2D graphics in different ways. It's kind of like a dolphin and a human being are both equally evolved, right? They've taken the same amount of time to evolve over time, but they're different things, right? So 2D graphics can be experimented with in very interesting ways and advanced continuously. So we haven't hit a pinnacle of 2D graphics yet. People have kind of forgotten about it, I think, But there's a lot of very cool things you can do with 2D graphics, and that's kind of what we're kind of doing with this fractal auto-tiling engine. Anyways, backwards deduction. What does this say? Backwards induction. Ooh, I mean induction. Backwards induction is the process of reasoning backwards in time from the end of a problem or situation to determine a sequence of optimal actions. The process continues backwards until one has determined the best action for every possible situation, for every possible information set at every point in time. So we are doing something like that, but our chain isn't branching. So I guess for when I said backwards deduction, I actually meant backwards induction. So let's change, so Q mean backwards induction. So that was my mistake. I thought it was backwards deduction, but it's backwards induction. I honestly don't know the difference between induction and deduction. I guess I'll have to look it up. Hey, we can look it up now. Deduction versus induction, right? So what's the difference between deduction and induction here? Inductive reasoning is the opposite of deductive. Oh god, they're complete opposites. Oh, well. Okay, well, let's look at it. Inductive reasoning is the opposite of deductive reasoning. Inductive reasoning makes broad generalizations from specific observations. Basically, there is data, then conclusions are drawn from the data. Even if all the premises are true in the statement, inductive reasoning follows the conclusion to be false. So really we're not doing general statement or hypothesis. Yeah, I don't care. Look, I feel bad for you, but I'm not going to lower my virus shields for you. Deductive reasoning. Deductive reasoning is a basic form of valid reasoning. Deductive reasoning, or deduction, starts out with a general statement or hypothesis and examines the possibility to reach a specific logical conclusion. According to California State University, scientific method uses deduction to test hypotheses and theories. Deductive inference. We hold a theory based on it, and we make a prediction of its consequences. You know, I think we're not using deductive reasoning, and we're not using inductive reasoning. We're just backwards reasoning, right? Because we're not like taking any types of sets of variables and whittling down. We're not whittling down from a broad conclusion, and we're not like going the opposite direction either. I think we're just backwards reasoning. Is this out of control? Deductive reasoning? Or is it inductive reasoning? Or is it just backwards reasoning because it is a linear chain? So I really don't know what the answer to this is. Right? Like what the heck are we doing right now? So, but we know that our backwards reasoning, whatever the fancy term we want to put on it, it's getting out of control, right? One thing's leading to another, which is leading to another, which is leading to another. Even though it's not branching out of control, it's still going linear. It's still going linearly out of control, right? So there's no decision branches, but one function leads to another function, leads to another function. It's out of control, and we have to stop it somewhere. So we're going to stop it here. The next thing is, we're not going to create this get brush state, so let's make absolutely sure it's nowhere. And then we're going to take the put brush state function that we're referencing here, find where we're declaring it, and then we're going to create the... I know we just said we're not going to create it, and I'm not lying, but what we're going to do is we're going to just say, you know, error, I don't need a helper function for my helper function. That's kind of long of an error message. let's just put this comment over here and just say, I don't need a helper function for my helper function. I don't need a helper function for my helper function, right? So there, we have a little acronym. And then we can also make a little timestamp of where we are in the video and say, you know, at vid IID, and we're at 0077, and the time is 1 hour, 20 minutes, and let's say 14 seconds. So I don't need a helper function for my helper function. So this get brush state, we never actually want to fill it out. We're just going to throw an error and say this random cryptic thing, right? And we can also say the year is 2020. If we need a little thing to... Ooh, it's not 2020, it's year 2021 now. But the reason why we're not going to have a get brush state is because put brush state was created to help test a unit test function. And now we're trying to use this get brush state to help test put brush state, and it's like, that's out of control. That's out of control. We have to stop this chaining of function creation of this function is needed by this function, and it's spiraling out of control when all we wanted was this one function that we're going to test, and now we're writing all these helper functions, and then this helper function needs a helper function, that helper function needs a helper function. We got to stop at some point. So we're going to stop it now. We're going to nip it in the bud because we see this pattern of, oh god, everything's starting to spiral out of control, and we're never going to use this function in any circumstance except for the test code if we had it. So we're just not going to do it, and we're going to long-handedly code what would be get brush state into the unit test function itself. Now we need an error macro here because we defined we used ERR there, so we got to define ERR and say AAC 2020, and it is PAINT5D, the subsystem, and then halt. And now we have a fourth macro, so we'll label that as 4. And then we'll take this with us and go down to the bottom of this section. Okay. And we'll undef it. So undef, error, remove this junk at the end of the undef because the compiler will not like that. And what else do we got to do here? So we got all this stuff, and oh wait, we're at the bottom of this section, so we got to jump our way around. So let's just go jump over here. Here's this thing that we're not going to use. It's referenced in one place, right? It's referenced here, so we can, bam, right back where we were. We're writing this long commentary about how we're not going to create a get function. We're going to say in here is basically inlined function. Right, technically we have this function, but it's kind of inlined here, right? We're going to just inline that logic. We're going to inline the logic. This is kind of weird to look at, so let's kind of like add a little bit more dividers so that we can kind of get a feel. Like, we're losing... There we go. That's kind of nice. There we go. It's a little bit ugly. Okay, so for the getter for this, we got to look at the functions that we're going to use, and the main function is not in here. It's actually in tau depot, right? Because we're going to directly grab all of those variables. Well, it's tau depot, but it's the tau depot functions. My bad. So right here we have this get function. So we're going to grab this, and we know that we're going to need to use it 7 different times. And since we are going to use it 7 different times, why don't we just kind of like define some things? So tau. Right, we're just going to grab all these things, right? So and now even though we define P5D, it's not going to affect this because the token needs to be, this is one token here, right? So the preprocessor doesn't like do substrings, right? So this preprocessor that's looking for P5D is not going to edit. It's not going to touch this, right? Because it's not going to do a sub token replacement. That's not how the preprocessor works. So now the next thing is for this last thing, we don't really have anything we can do with that. Right, because that's going to be all the different defines. Well, hold on. Let's do T, P, and then define actually, let's do tau depot like this. Sorry, I'm changing my mind here. So I'm thinking we do this. I'm just kind of annoyed by how much space we've been losing here. So we could do like this and tau depot dot PAINT5D, or not dot tau, right? So we're getting it from the tau. Then it's TD dot. No, I don't like that either. We can do that. We can do that. It's just right, so let's do tau, and then PAINT5D, right? Let's just do tau, PAINT5D, and this is tau depot, so then we can do tau depot dot, and then this P5D whatever. This is not going to be VP1 though, it's going to be like a TQ right there, TQ. So, you know, dex sub and var is what's going on here. And then we can just make a note that this is get, and we could also write like a TQ here if we want. I don't know, we're getting a little fancy here. So we want to get TQ, TQ is right there, and if we highlight this, both of them light up, so that's nice. So also TQ needs to be here, right? Are we doing TQ? No, we're using... Oh, fuck, we're in the wrong section. Are we really in the wrong... Oh, no, we're not in the wrong section. I'm just forgetting all the code I wrote for this. Yeah, that's right, we did write all this code. Jeez. So got TQ, got whatever. Okay, so we'll just say, you know, got TQ, and then if we highlight this, I think everything should highlight. Yeah, so these three things highlight, so that's kind of nice. And then this is unused 1, 2, and 3, right? So, and we actually need to use unused 1, 2, and 3. We can't just use a one unused variable because we're using the restrict keyword with this, and we don't want that means that each one of these pointers needs to point to something that's actually different. So right here we have our maybe we don't have them. We need them, but we didn't use them yet. Okay, we didn't declare those yet. So let's look. Declare iterator vars, test table members. I guess to keep up with this, we're just going to say declare unused vars. Right, so we're literally declaring unused variables. And hopefully we're smart enough to make the assumption. No, actually, we have enough room where we don't have to make the assumption on what it means, so we're not going to, right? We have plenty of column space for this, so we'll just say that this needs to be a U32, and it needs to be called unused 1, right? Unused number 1, 2, and 3. So 1, 2, and 3. 1, 2, and 3. Okay, cool. And we'll token highlight all these so we can make sure that we see those 3 unique colors in the place we're using them, and we see 1, 2, 3. Excellent. So I think those bars kind of look like L's a little bit too much, so we'll do this. Excuse me. It also might be kind of nice to just give the space to breathe, and just put it over above here like this. Technically, the variable is TQ, so you might actually want to write it like this. TQ. Right, so TQ is... Oh, but if we write it like that, we can't get everything to highlight, can we? Like, if we do this and we try to highlight everything that's TQ... Oh, interesting. That works. I did not... Whatever, it works. Okay, we're good. As long as the token highlighting works, then we'll call it good. So, right, we kind of condensed this a little bit. But you know what? If we want to... We're gonna get rid of the underscores on the unused, just because I would like to try to indent this a little bit more. And in order to do that, we're gonna have to scrunch everything up a little bit. Tau, P5D, PAINT5D, and then the actual PAINT5D variable. So if we want to see the PAINT5D variables that we're looking at, we should have them. This is PAINT5D data. Oh, this is Tau, though. It's in Tau. So in Tau Depot's data. Okay, so TQ, these are all the variables right here that we need to use. Or all the locations of the variables, I should say. So P5D, okay, so that looks good. And we could kind of move it like that, sure. Okay, so let's paste this a few times. So 1, 2, 3, 4, 5, 6, and 7. Right, because there's 7 different variables. We could also keep a checksum, right? So we could do a, this is var. If we wanted to keep that pattern, we could just say, you know, this is var 1, then we want var 2, var 3, var 4, var 5, var 6, var 7, and we did too many pastes. 2, 3, 4, 5, 6, and 7. Yes, it does appear that we did one too many pastes, because there's 7 variables, I know that. So let's just do, we got TQ, the next thing is TE, so TE. Okay, the next thing after TE is TL, so TL. And L is on the other side of my keyboard, so that sucks. Okay, after TL, it's BX and BY. Oh, yeah, that's right. Right, so this is BX. And that kind of makes things kind of confusing. I know why that is, but that's local X. So we could make a note here that, you know, LX equals BX here. So that way we have a BX highlighting here, but we can use this as a LX. Or, right, so that just way we can see the LX highlights, and we see LX equals BX, so then we can highlight that, and then everything kind of shows up there. Is that the way we want to do it? Because these are all capitals, so technically this would be the BX, and then, sure, we'll do that like that, and this would be BY. Now, this is brush Y. And, yeah, we have a little bit of fractionation of our variable namespace, which I'm not happy about, but I guess it's bound to happen. So BX, BY, and it's the variables used in a slightly different context. So they have the exact same meaning, but they have a different context. So I don't know. I would like them to have the exact same variable name if they mean the exact same thing. Does context change the meaning when it's the exact same data? I don't know. Yeah, whatever. So BY, this is LY, and then we need a little note here where we just say, you know, LY equals BY, right? Just a little note here so that when we're looking at this code and being like, here, there's this irregular part to this, we can actually do like this, pattern, right? We can actually hashtag pattern breaker, right? That's kind of what we use in our code in other places, so we could hashtag pattern breaker in here to say, hey, this is a pattern breaker. Yes, we know that it's not quite the way it needs to be, sorry, right? So, okay, so this is going to be AD, and then this is going to be AD, and this thing over here is going to be got AD. Then TV, right? So this is TV for tile value, and this is TV for tile value, and this also needs a TV. So now that we've kind of put that all in there, let's use these to kind of check. So 3 things highlighted, 3 more things highlighted, 3 things. Ooh, that kind of sucks. So we can see this TL is right, not the. Okay, whatever. Let's just start back from here. So BX, 3 things highlighted, and if we do LX, we can see these 2 LXs, the LX equals the BX. That kind of sucks with that indirection there, but we have it. So 3 things highlighted, and then if we do this here, we see, oh, and here's saying that the LX equals BX, that's fine. So AD, 3 things highlighted, TV, 3 things highlighted. So all these things are in order, right? So this is an inlined version of PAINT5D get brush state, and we never actually create this actual function, because we only would create this function to help test our helper function, and the helper function that we're testing right now is just a helper function for a function in a unit test. So right, it's getting out of control, so we're just going to inline this, right? So right, and we have the little commentary of why we're not going to do this, and so at vid IID, let's just do this one more time. It is 1 hour, 36 minutes, and 30 seconds, and we'll just say, you know, why is P5D get BS inlined here? So yeah, we'll do something like that, and we'll kind of describe it one more time, because we just want to have kind of a paper trail, right? We can always remove commentary later, but we can never add it years later or even months later after we forgot our thought process in the moment, right? So we're going to take this, and we're going to change that timestamp a little bit. So let's say 1 hour, 37 minutes, and let's say 25 seconds. Okay. So why is P5D brush state inlined here? So why is this function, why is it inlined right here? The reason it's inlined is because this is a helper function for a helper function whose helper purpose is just to help test unit test code. So it's getting out of hand. We don't need a helper function for our helper function, you know. So we have to stop it somewhere. Otherwise, we're just going to get this chain of pointless unit tests functions, because we're getting to the point where we're not actually unit testing the code we want to run in production. Does that make sense? So now that we have this little hashtag, we're also going to go into here and also explain it in here. So we'll do this, and we'll say, hey, why is, you know, blah, 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 right? And we'll describe it one more time. So that way we just have it in a lot of different places. We've documented the heck out of why we're doing this crazy thing. So, code body exists as a section of inlined source code within the unit test. So it only exists within this unit test. What is this unit test? What is the name of this? Within the unit test, because itself is a helper function to help run a unit test. I don't want a helper function for my helper function that I then have to write a unit test for. The backwards reasoning chain needs to be nipped in the bud now before it gets out of control. Okay, so this is why, and then let's make a commentary. At vid IID 0077, and the time is 1 hour, 39 minutes, and we're do 40 minutes, and 5 seconds. Okay, so the P5D get brush state is inlined here, where we're referring to this commentary, because AAC 2020 PAINT5D get brush states code body only exists as a section of inline source code within the unit test. PAINT5D unit test code put brush state. Oh, it exists within here. I'm not reading this correctly. Okay. The basic summary here is we don't want unit test code for our unit test code. And because we have a helper function for our helper function that's used to help check the validity of unit test code, if we end up creating a get brush state function, then we inevitably have unit test code for our unit test code. That's kind of what that means. Because the put brush state is only used for unit tests, and if we use this get brush state to help test the put brush state function that only exists for the unit test, then essentially we have unit test code for a unit test code. We don't want that. I don't want unit test code for my unit test code. So if that makes sense, hopefully I've explained it enough times. Let's get back into the actual code that we're writing. So put brush state, where are we? This is the unit test code, UTC, unit test code for put brush state. Here's our test table. Here's all this craziness. Here's some comments. This is the inlined version of it, and these should be, tau depot get always gets uint32 values, so the got values should be u32s. They are u32s, excellent. So we changed these to, instead of u underscore, we changed it to u1, u2, and u3, just so that we have a little bit more space where we're calling these functions, because we got a little bit out of hand. Right? We wanted to condense this because these are very verbose, so we're like, here, let's just kind of condense these to the macros of what we need. And since we're doing that in this section, the next thing we need to do is at the end of this section, we need to undef every single one of those macros. So undef, space, these things. We should also make a note that there are 3 of them. So 3 of these macros, and we're undefining them. Okay, so 1, 2, and 3, and then over at the right, 3 isn't really too much to count, right? It's not like visually you can see when 3 is 3 without counting it, so it's not really necessary. But I do like to keep up a consistent patterning with my code. So we're running out of room, so we're going to have to use a comment style like this rather than the comment style with colons, just because we're running out of room, and I absolutely do not go over my column limit unless it's for to-do messages, because to-do messages are, it's okay if the to-do message annoys me and kind of sticks out like a sore thumb, but if it's production code that's already finished and done, it should not go over the column limit. So tau, P5D, and TD. So let's just highlight these really quick and just say, hey, are these all correct? Yeah, that looks correct. So we got the brush state, and this is inside of get test table members. Yeah, because so this would also be, we might want to label this one more time and call this put test table members. Because we have we have this thing called get, so obviously there's a thing called a put, right? So let's do that. So in here, right, so it's a little double labeled, so use or put, same thing, right? We're using them, but we're also putting them. Now, in this other section, we're not going to do that. We're just going to say get test table members. And then the next thing we want to do is check test table members. Do we want to keep that same pattern since we've been doing it? Yeah, sure, why not? Let's just right, we're being weird, but if we want some consistency with how we're doing that, we'll just say chk test table members, right? So that we have kind of like this consistent labeling. And here we're just going to check that the things that we put are the same things that we got, right? And we know that when we get things, we're getting the U32s out because they're encoded in pixels. But these values here are U08 values, right? They're U08s. Yeah. So let's, we're going to have to downcast some things. So, we're just going to say, you know, if 0 or a U08 cast of one of these got values. So got, let's go with the first one, TQ. So if this is not equal to, TQ is already a U08 value. So we can just do this. We don't have to downcast it. And then 1, 2, so there's 3, there's 4, there's 5, there's 6, there's 7, okay? And now that we have all those in place, we should just be able to kind of grab these, right? Kind of grab and just kind of paste, right? So just be like bam, paste, and bam, paste that there. And if any of these things are not equal to each other, then we've kind of failed at something. We want to say, we're not going to do a print off of what they are. We're only going to do a print off if it actually fails and inspect further. But yeah, we're just going to say that unit test fail, and just say the date, 2021 0106, and it's 3:58 a.m. I'll just do UTF for unit test fail. I'll just say so in this specific instance, UTF is unit test fail, right? That's what we mean by UTF in this specific instance, right? This just needs to be unique. It does not have to be informative. It just needs to be a unique message. The informative part comes from when you look for this exact message in the source code and see all this stuff, right? That's the informative part. The error just needs to get our attention and make us find the offending code within the source. So, okay, so we have this function, and it looks pretty good to me. And this is a test function, and I'm actually fine with just doing this. Because, yeah, I'm fine with these tests. I don't really feel like I want to write any more tests. I mean, if these pass, I'm satisfied. I want to get done writing test code. 24 plus 1, because there's this 24 here, plus 1 to get the total number of tests, because we zero index these. The number of columns, 7. Is 7 still the number of columns? 1, 2, 3, 4, 5, 6, 7. That checksum checks out. Rows times columns. Excellent. And then rows and columns are undefined at the end, correct? Yeah, they are. Okay, cool. So, what's next? It looks like we have the unit test code for both of these. So we have the unit test code here, but we were working on this, were we not? Okay, so we need the put using brush. And this is the test code, put using brush. So put brush state and then put using brush. So to put using brush, we're actually going to use put brush state. And then we're going to, yeah, right, it was just spiraling out of control. So that means we're going to inline all this code again. Yeah, whatever, that's what we're going to do. I do not want to have to write test code for it as well, and so we're going to inline it. Again, I don't care. So for put using brush, what we could do is, right, we're going to put the brush state, and then we're going to just put using the brush, right? So let's take all this stuff. Let's take it all and cut and paste it for a second. Okay, We're going to take it all. We're literally going to take all of it. We're going to cut and paste it here because it's really redundant, what we're doing here. And we're not actually trying to get the brush state, though. We're trying to just get the pixel value stored in the current location defined by the brush. Yeah, that is true. So getting these test table members, we're going to remove this. We're going to remove that. Actually, no. We're going to keep it. We're actually going to keep this because it has a little bit of redundancy that could help if we add more kind of tests to here, then that could help. Well, the thing we want to actually test now is put using the brush, right? So put using brush. So let's highlight this for a second. Be like, are you being used anywhere? So this is copied from this code here. So we'll keep that timestamp comment, sure. But we probably want to make a note that, you know, that block comment was kind of copied, right? So a lot of this is just kind of very redundant copying stuff. Sure, we'll inline this again. Why not? It's test code. Redundancy is okay. So we'll check the test table members, and then actually put using the brush state. So we need two new sections here. We need to actually put using the brush state, and then we need to fetch tile value using we need to fetch the tile value that was put. That's the next thing we need to do, right? These are the new sections. Okay, so the function we're testing is put using brush state, is it not? It's called like put using brush state? Yeah, so, or put using brush, whatever. And so it doesn't have any members, right? We're just checking that everything's set up correctly. So put using brush, and then this is void. And it's AAC 2020 PAINT5D, and then put using brush, and this is void. Well, I guess we'll just do this because we don't have much room. So put using brush, and in our PAINT5D notes, it should be in here already, but let's see. Yeah, put PAINT5D, put using brush, right? So this is needed to test toggle tile, right? So these are functions that are only used for our unit test code, and that's why I don't want to create functions to actually test these as well, because it's just spiraling out of control at this point. Okay, so put using brush, and the next thing we want to do is we just want to get the value that's loaded in there. So we're going to use this PAINT5D get to get the tile value, and we're just going to check, hey, did that work, you know? Okay. Excuse me. Oh, God. Ah. Okay. So the tile value looks like it needs to be a pointer. Are we already using these kind of long-handed variables, or can we just declare these? Let's kind of scroll up here and be like, what do we already use here? So we have this, and then we have this, And then, so we can actually say that these values are UO8s. So we can say declare values for let's call it vars for. All right, so these are specifically for this get function that we're testing, right? Right, it's a little bit of a weird section name, but we want to keep the declare this, declare that, etc., and keep that kind of section naming. And then also, if we highlight this, right, if we highlight it, we should be able to see, oh, not put using getBrush, but PAINT5D, whatever. So yeah, we can take the variable names here, and we can just, oh, but they're UO8s, so there should be 7 of them. 1, 2, 3, 4, 5, 6, 7. And we can take all these. So you see the last one is a pointer. That's because it's an output parameter, so that's fine. And because we're already going to test these need to match, we can compare directly against the UO8 version. So we'll just say, bam, there you are. 1, 2, 3, 4, 5, 6, 7. Okay, so we should actually use a trap value, because if not, we're going to sometimes get random failures or random successes if we don't use a trap value. So we should actually just, like, you know, whatever, the trap value doesn't need to be something specific. It just needs to be initialized to something that's not random. So it's not really necessarily a trap value, but, you know, non-random initialization. And then we're going to use 255. But 255 shows up a lot in code, so we're not going to do that. We're just going to do like a, I don't know, how about 409? No. How about 409 is too high, that's why. How about 204, right? Or, yeah, 204, that's less than 255. So now that we have these values, we can copy all these. And also we can make a little checksum here as well, and just make a note of, hey, is that everything that we need, right? We can also make a note of what the shorthand variable names are right here as well. Okay. Okay, so let's take this and let's actually run that getter function. So we already have them, but remember that last parameter is the output parameter, right? So we want to use an AND symbol here. And as far as these explanations, we're out of room, so we're not gonna add the explanations. We have the explanations all over the place in other places. It's just a bonus when we have room for it, but we can take these guys, right? Because that's what they're supposed to be. TQ. Tile X, tile quad, tile exponent, tile layer, the local X, the local Y, the offset dex, and the tile value, right? Cool. So now we just want to say that, you know, if 1, and we copied and pasted this test code. Does that mean that the test failure message is in 2 places? Hold on. Yes, it does. So this should be, instead of 3:58 a.m., it's going to be 4:10. 4:10 a.m. There we go. So unit test fail. Then here, you know, if 1, or actually not if 1, that means it would always fail. If 1 or this thing is UO8 is not equal to TQ, right? And then we'll just see a 2, 3, 4, 5, 6, 7, 8. And then we can take this, paste this over here, take these, paste them over here, and then have a little checksum to say, hey, do we have exactly 7 things? We have 7 things here. Do we have 7 things there? If we're going to put it in here like that, we might as well continue with that. If that's the way we're going to roll, then let's roll that way. That's fine. Though, I mean, if we're going to do that, I feel like we're using too much of this blue blue coloring, so we should knock that off. And maybe we're getting too crazy over here. I don't know. But yeah, so just make sure that we have these two checksums here. They're both 7. And this is actually in a big if statement, so have an error message and just say, you know, error. I don't know. So that's my error message, right? It just needs to be a unique message. Maybe we'll do that more than once, but we're hoping that the random BS messages that we make aren't going to conflict. And if we also put the year, we're hoping that, you know, within 1 year that we don't do any overlapping weird messages like this, right? It just needs to be unique for the code base. So yeah, I mean, that's our test for this, right? It's just a cut and paste of the previous test code. And then, yeah, we just test to see, hey, we're going to get a value. This is getting a value encoded in the, get a value encoded in the bitmap / texture. That's what this is right here, right? We're actually getting a value encoded that we encoded in the texture data. And then here we're just, you know, checking it, right? So check that proper value was encoded in the bitmap / texture. Right, then we just want to check, make sure, hey, is the correct thing put there, right? And then we can also, we also have enough room where we can kind of indent these. So this label, it's a label, and then we indent, and then we have this label, and then we indent again, right? So we have enough room for it, so let's do it. Okay, so good. So we have, but remember, we got to remember why we wrote these, right? Right, because we kind of spiraled off into these. This leads to that, that leads to that. So why did we actually write this? And we need to get back to, well, why did we write this, right? And we wrote it for, well, let's look at where it's called. So it's called unit test controls. And if we look at where this is called, it's called in the middle here. So the unit test user controls is unfinished as far as I'm concerned. There's probably like one last thing that needs to be, oh boy, that's not good. So why the, ooh, what the, how, ooh, that's scary. Ooh, that's not good. Ooh, that's really bad. Did we change the casing maybe? Well, hold on. This says user controls. This says prog controls. Did we accidentally... These are definitely the user controls. I think we named... Fuck. Prog controls. Do we have two functions? Move camera, zoom camera... move brush, delta mutate. We got these things, so move camera XY. And then we also have it like these things are not, these are pragmatic controls here. Right, these are the pragmatic controls. UTC put, UTC get. Right, and this thing is not prog controls, it's user controls. It's even in the user controls section. How the fuck did I... This is what I'm talking about, where you gotta have unit test code, because you make stupid mistakes, and so you need the unit test code, because sometimes you just do stupid things. So, so user controls, these are the user controls. toggle tile was the last thing we were testing that kind of led to this spiraling chaos of a whole different unit test section. Yeah, right? Toggle tile is the unfinished stuff. And we gotta finish this. So, did we leave a little define here or something to say, hey, yeah, finish this toggle tile? Excellent. So we have a little define for, hey, finish this. So what we're gonna do is we're gonna run the code and try to fix any mistakes that we made in other sections until we get to this error finish test toggle tile. Because I know that most likely we made some mistakes while we were coding those other functions. And so let's start the process of... God, this is so much code, right? This is like the 9th, 10th video. This is the 10th video on this system since we started the sprint, and we haven't gotten any working code yet, so that just sucks. Okay, stray at in the program, so we cannot do an at symbol here. So that is in PAINT5D put brush state. No. Oh, no, it's in the data file. That's where I would expect it. I just don't... Okay, so this is just a token that it's not actually defined anywhere. And we can make a note here. Means depends on tile exponent. So we cannot have a single max value. So this depends on the tile exponent that way, and that's why we can't have a single max value for the local tx and local ty, because that max value is going to change depending on what the tile exponent is, like what size tile we're painting with. So we can make a note of that while we're here. So at vid IID 0077, and the time is 2 hours, 6 minutes, and 48 seconds. Let's do 55 seconds. And then restate for the camera what's going on here. So this little abbreviation that's called depon tile exponent means depends on tile exponent. This macro here is never going to be used. If we use one of these, it's going to cause a compile time error because we're hoping, because we can't use it. We cannot use these values because there's not just one limit for tx and ty. That limit changes depending on what the tile size is, defined by the tile exponent. So if you're using one gigantic tile, then the limit for tx and ty is just 0 and 0, because there's only one possible coordinate for that gigantic tile. If you're using very, very small tiles, the smallest tiles, then the limit is 127, right? Because you have a 128 by 128 region of the smallest tiles. Okay, so that's good. Let's rerun this and see what we can do. And then I had something else on my mind. Oh, so it is like 2 hours and whatnot. I decided that in addition to the push-ups, we're also going to depon tile exponent is undeclared. Oh, really? So we can't do that? Okay, that's fine. We can hack this. We're gonna just hard code this as a string, right? And then we'll hard code it here as well. And that's just a little hack, because it looks like we can't use a unidentified token. But now it's just a hard-coded string, and a hard-coded string where we're expecting a integer, right? That's immediately going to fail, so that's good. That's fine. It's hackish, but it's pragmatic. Comparison between pointer and integer, really? Okay, 12,000 and some change, so, oh boy, just look at all this stuff. This is just ridiculous. Is it still unit test code when we're in the 12,000s? Yeah, this fucking sucks, man. Oh, no, we're not in the 12,082. Assert LX Greater than or equal to 0. No, they're talking about this less than or equal, so this ly and this max ly. This should not be a pointer, but I could be wrong. Well, why is it specifically once we got to lx, right? It didn't fail until we got to lx. So what is it about? So what is it about the lx, and I'm assuming the ly as well, but let's look at lx, because that's the first thing. Now, it could be a problem here, but I'm going to guess it's a problem here. I-32, oh, maybe not. It's because, remember, we actually triggered this, right? Because we can't, right? That depends on the tile exponent size. So we can't actually use this. So what we'll do is, let's kind of blank this one out. Let's blank these out. The max, let's blank them out like this. And then, let's just do, you know, so what's the size of these? What's the size? Okay, int32. Brush state. Let's just do it right here. int32 and max. And let's do lowercase, right? So let's change these ones. These are not macros, so let's change this to lowercase. So we still have them. They're highlighting, but these ones aren't macros. And this one is going to equal max lx and max ly. And just, we'll have some branching logic here. So we'll just have like a, you know, if tile exponent, if 0 equals the tile exponent, then max lx equals 127, and max ly equals 127 as well. Right, it varies depending on the tile exponent. And then we'll just do 1, 2, 3, 4, 5, 6, 7. We know that's what we have. Otherwise, it's 0, and it'll be like, hey, what's that about, right? So let's just do a 0 minus, how about 1, 2, 3, 0, 1, 2, 3? Something like that. Make sure it's absolutely set. And let's continue to go 127, 63. This one is 31. This one is half that, 15. Half again is 7. And we're missing something again. Keep on doing this. Half, half, half. Because 8 and 8 is 16, right? 7. And then this should be, maybe we're not. So half of this, 4, 4, and 8. Half of this is 1. Oh yeah, no, we're not. Right, because one gigantic tile for the largest tile exponent, the only coordinate can be at is 0, 0. So that is actually correct. So let's actually add 1 to each one of these things to make sure we have powers of 2. This is 1, 2, 4, 8, 16, 32, 64, 128. So that's correct. Okay, so we have a lot of redundancy in this, but that's okay. But we might actually want to make some defines to be like, you know, if defs for these checks. But right now, we're not going to worry about trying to shut off our error checking code until we're ready to kind of like optimize for performance as far as I'm concerned. So this check, that check. Okay, cool. So we have these checks here, and we're just not even gonna, we're just gonna keep this same checksum to 7. It's just that we commented out these defines because of this nonsense over here. Okay, cool. So let's take that for our run. And I'm gonna guess we're gonna get another error for this, because I bet if we actually copy this, right, we probably are in the, yeah, we have the same exact code again, don't we? So it's nice that we kind of commented everything to be very analogous, because we can easily jump to that section and be like, oh yeah, we need to actually write some code for this outputs as well. But first, let's make sure that we get to that section of improper code before we start fleshing that out as well. So, error, AAC Tau Depot public library struct has no member P5D LX. Now, is that true? Yes, that is actually true, because it is called brush X when we get there. So let's find this thing called LX, and we'll just say, you know, I don't know what we want to do for that. I guess we'll just say BX. DLX. So we can make a note here that, you know, this thing is equal to this thing. And we can make a note that this is a pattern breaker. Right, because there's some inconsistency here. So we can note that, hey, this is a pattern breaker. Now we also have another pattern breaker down here. Right, because this same thing, this is brush Y. And we'll just say, you know, P5D Ly is equal to P5D brush Y, right? So this is conceptual. This is what it actually is. Also, this goes down one line. Then we'll also do the Ly equals, and then By, right? So that way we can also highlight these and go, here's our Ly, here's our Bys, and everything's highlighted. Cool. So let's continue. Let's move forward to the next things. It kind of sucks that we have some inconsistencies, but oh well. So large integer implicitly truncated to unsigned type. Okay, well, let's take a look at this. This almost looks like a complete Well, let's take a look at it and see what we got here. So just right here. So we have this U08 tile quad, and oh yeah, so if these are U08s, then we can't use, probably just cut and paste it, but we can't do this. This is ridiculous, right? We cannot, we gotta like do like, if we really want to do that, we could do like 100 or 101, 102, 103, 104, 105, 106, 107, right? We can these could be trap values. We can't go over 255 on this, right? So there we go. Okay, cool. So now let's look at what we got next. Without a cast, some type of conversion. The unused are U32s, but when in that function, maybe it's not, we're using the wrong type here. So let's look at this. I'm going to guess they're U08s, not U32s. No, these are definitely U32s here. Makes pointer from an integer without a cast. Oh, right. Just because they're unused doesn't mean that we're not going to use the pointers, right? So we still need them to be pointers. We're not going to use them, but that doesn't mean that we can call them any differently, right? So just because they're unused doesn't mean we can, right? That would be, I'm glad the compiler caught me for that, because that would be disastrous if it let me do that. Because essentially what you're doing there is, especially because these unused are like that, we were essentially kind of sending random memory addresses to these functions. That would have been horrible. So now, even if we, yeah, that would have been horrible. To help protect against that, I guess what you could do is you could initialize these to 0. so that if this function, if the compiler wasn't able to check that these weren't actually addresses, but they were just values, well, the value is 0, and that evaluates to a null pointer, and hopefully the get function would have some logic to check for those null pointers and be like, hey, that's a null pointer, and then crash, right? So we're going to say at vid iid 0077, and the time is 2 hours, 19 minutes, and 50 seconds. We're just going to say keep U1, U2, U3, 3 initted to 0. This is not actually a section, this is just a commentary in all capitals. We're going to keep these variables initialized to 0, these unused 1, unused 2, and unused 3. And the reason we're going to do that is because we forgot to use the address of operator. And if the compiler didn't catch us, we'd be in some serious trouble because we'd be shoving random memory addresses to these functions as output parameters. That would be horrible. It would just get horrible, unpredictable results. Luckily, the compiler does catch us, but just in case you were compiling on a system that doesn't, or we want to make measures where if the compiler doesn't catch it, we'll be able to catch it. So by these being 0 initially, if we don't pass the address of, then we'll be passing null pointers effectively, and hopefully the null pointers would be, you know, caught by these functions. Okay, cool. So we've described that twice in a row. We're good. We can keep on going, I think. So now that we're here, we might as well be like, hey, TQ, TE, TL, TY, or not TY, LY, and, oh, okay, that's, yeah, I was like, wait, where's my, okay, there's my X. X, Y, and local X, local Y can also be seen as brush X, brush Y. And also, I don't think there's actually a P5D LX. We actually have to fix that. It's going to show us. Let's kind of recompile here, because it's probably going to complain at this line, because I don't believe there's a LX. Yeah, so there is, it's not LX here. It's called BX, right? So, so this is, P5D LX equals P5DBX, and then we'll make a note that, you know, LX equals BX, right? Same as the, right, we've done this before, hashtag pattern breaker, and whatever we did it in before had a little bit more room, didn't it? Because, yeah, we used, like, we didn't use the underscores. I don't know if call it pat breaker. Let's just call it pat breaker, and we'll just make a note of that. That if we see pat breaker, it just means that it's shorthand for pattern breaker. Shorthand for pattern breaker. We'll just use that so we have kind of room to write it without going over the call limit. And let's make sure that we haven't actually created this before. So pat breaker, only in 2 spots, awesome. Now if you go to pattern breaker, we should be able to see, also known as pattern breaker. So yeah, we have, yeah, there it is, pattern breaker, okay. Pattern breaker is a warning to reader of code that something about this code breaks the conventions/patterns typically used in the codebase. Okay, so that's fine for me, right? We're trying to spot out inconsistencies and be like, this is inconsistent. Take a look at it, right? So this is going to be Y instead of X. And then we'll take this pattern breaker thing, we'll put it over here. Pat breaker. Okay, so AD and AD, tile value. We can also make checksums here as well. So we have room up at the top right here. We have some extra room, so why not just be like, you know, this is, you know, variable number 1, 2, right? We should have 7 of these. So why not, you know, add some checksums while we're here? Be like, we have this code needed attention anyways. Let's make it even better. Okay, so the checksums check out. There are 7 things. That's what I expected. Let us keep on going, and now we're kind of jumping all through the code. But remember, we're going to keep on jumping through the code until we get caught by that preprocessor error we put in the code, the preprocessor error directive. Okay, tau depot blah 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 has no member P5D ly, and that is true, and it's because we forgot to rename this as brush y. Okay, cool. Okay, now we're ready to keep on checking for more problems. Okay, so we got U1, U2, U3, and once again, we forgot to right, just because we're not going to use these values doesn't mean we don't need addresses. And we were kind of in the middle of that earlier, weren't we? I think. So let's fix this. Let's fix that. These unused variables are kind of starting to take up more room than I would like. I'm not sure how I feel about the alignment on this. I would like to keep it all... that's kind of bad. Yeah, so let's think about this. Let's think about our life and our decisions. So this is okay. Right, 4, 5, checksums, etc., and symbols. Wait, okay, because we're being... ly, so these line up, these line up. That's fine. Okay, we're good. We were just trying to adjust things that did not need adjusting. Is that what we were doing? Yeah, that's what we were doing. Okay, cool. So let's give that a run. See what else we have screwed up. Also, are these initialized? Okay, so A is for assert, blah, 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 something, something is going on over here. And I know exactly what's going on. So it's this stuff here, and remember, we have this section labeled analogously. This is the outputs. We have the same thing for the inputs, and we notice, hey, we got all this crazy stuff. Let's take all this crazy stuff here, and let's go over here and range check extracted variables. So, right, this is because the max changes. So it's an int32 comparison, and so is this an int32 then, or what is this? I guess these might be like greater than 0, so these maxes are probably U08 values now, right? So if we look at, yes, these shorthand ones are, these shorthands are U32s. Okay, yeah, so if these shorthands are U32s right here, then we're just gonna say, hey, you're a U32 now. And now max is, we'll just say max is 0, because that's the most likely maximum to create a problem if we don't correctly assign these, right? So U32 max, and then here's our table for creating the correct maximum value. Now you'll note that the LX and LY, when we're comparing to max, we're going to do the lowercase max, right? So these are lowercase. And then where we originally made these defines, max LX and max LY, we're just going to comment them out. We're going to keep the checksum here. Right? We're going to do exactly what we did in that other block of code. The only difference is that the type here has changed. So max LX, max LY, we're going to comment that out as well. So sometimes things get kind of weird, right? Where it's like, why is this comment here? Well, that comment here is to preserve this checksum here, right? Preserve the ordering that we want to see. And then if you highlight these things, because you're like, oh, that's weird, you can see, oh, that's why this is commented out, right? Because it depends on the tile exponent. The tile exponent is going to change what the maximum x and y locally can be. This tile exponent, though, is that... Yeah, so we have I32s, etc., etc. Okay, so we're good. We're good there. Let's keep on going and see what we screwed up next. Okay, so we sealed off a function using a whole bunch of semicolons, and ISO-C does not like that. So let's do a Control-G, because it's pretty far away. 2377. And the reason I did why I did the actual go command rather than scrolled through it was because these can be kind of hard to find because they don't have much identifying information on them except for, you know, 2 semicolons. Yeah, so this is the unit test control is cool. So, okay, we'll just get rid of that and look for the next problem. And so on and so on and so on, right? So, Control-G and 2428. Okay, we're on 1 off, but close enough. So, lax comma has come to hurt us. So that first test, we can't have a comma in front of it, right? I'm sure we've made that mistake, and right, we cut and pasted this code, so it's probably going to be the next errors. One of the next errors will probably be that as well. Oh, yeah, you know, commas, we forgot all of our commas, didn't we? We were like, hey, commas, huh, what are those? So we actually need to align these with the bar symbols. Wow, we kind of... Right, the reason why we didn't put the commas in while we were doing this was it was kind of like a... Fiddling with the commas was kind of slowing us down. So we're like, you know what, screw the commas, we'll put the commas in later once we've kind of figured out the exact placement. With that, I do want to scroll down to the next test, because I know we cut and pasted everything. Yeah, so we cut and pasted everything, so we're going to have to... We could re-cut and paste, but I know we probably changed some of the values in here. Well, maybe we didn't. Actually, I don't think we did. But to just be safe, we're going to say, hey, just in case. Now, the first thing, right, this first thing needs to have... like that. Okay. So I think we're ready. Let's see what else we screwed up. So yeah, we're going to make a lot of identical errors in stuff. And 2686. Are we in 2686? How did we forget? Oh, so we forgot one line of... Okay, cool. So let's give that another run. See what else we got. Number of test elements. Note an expansion of macro. Here's all these X's. So that is, you know, that's true. I mean, we probably should have, you know, something that's not a whole bunch of X's, right? So that is, where are you? It was probably in the toggle tile code, right? Well, let's just go Control F and search for a whole bunch of X's and hope that there's only one place with that. Too many X's? Yeah, too many X's. Okay. So, yeah, right here, only places where there's a whole bunch of X's. And are we in toggle tile now? Okay, we're finally back in toggle tile, back to writing some test code for this toggle tile function. We have number of test elements. This is no use, right? Also known as unused 1, unused 2, unused 3. Are we satisfied with... Yeah, we're satisfied with the initial very simple test at first, because we're going to start off with a tile value of 0, a brush value of 0, and then we expect 0. If we do a tile value of 1 already in the system, already in the data, and a brush value of 1, we're going to expect a 0 back out, right? Because this tile value already exists in the data. So that means we actually have to put that value and then use the brush to set that value in the same exact spot that it was already put and see that the tile gets reset back to 0, right? It gets unset. If we have a tile value of 1, where the in the data, if there's a tile value of 1 in the you could say the tile map, and the brush value is 0, then do we get 1? Hold on. That's actually incorrect. So I see we're like trying to say, you know, if they're different. Yeah, this is wrong. So this is going to unset it. But if it's tile value 1 and the brush value is 0, then we're going to set the value because they're different, right? And it's what's in the brush there. So let's make sure. So this brush value, if we look at brush value, where are you being used? And oh boy, you're not being used anywhere, huh? That's a problem. Are perhaps we using some other long-handed version of brush value? So you have BV right here. So this is the mutator value. This is the must load into brush. Yep. And load brush with tile value. Put brush state. Well, first of all, this commentary is fucking wrong. This is actual. All these comments are wrong. Check against expected outputs. Okay, so let's think about this. We do want to put the brush state. This is a thing. We don't need to actually do this either, right? Because we're going to use this put brush state here. So doing this is no nonsense. Load the brush. So this is loading the brush is what we need to do. And when we load the brush, we actually want to use BV. We don't want to use we want to use BV. Right, so we actually want to use the brush value. So this BV here. And so this is all nonsense over here. So these are our initial values, right? These are initial values. These are what we want to extract here. And are there 8 members? What do we got? We got 8, 9. Ooh, we have 9. So these are the initial values, right? So this is overly verbose. So let's kind of clean this up here. So we're extracting the values that are loaded into the test. 3, 4, 5, 6, 7, 8, 9, or something like that. Bam. Okay, so okay. Initial values. So these are the initial values right from here. Initial values. Let's keep the same kind of writing here so that when we kind of highlight this, we can see it. Initial values, mutator value. So I think we need like 3 more things. So we have the maximum index should be 8. So 7 and 8. Okay, so this is the mutator value. And the mutator value is the BV, and the expected value is just EXP. Kind of weird, but mutator value is the bx, and then expected is this exp thing, right? So if we look at the ordering here, we should be able to like go bing, bing, right? Bing, bing, right? Should just be able to hit all these in the correct order and kind of see them light up, except for the BV. Oh, right, because we did BX, that's not correct. This needs to be BV for brush value. Okay, and then the exponent, right? So let's do this last section really quick again, since we had a problem. Okay, cool. And there are 9 of them, so the max index would be 8, 0, 1, 2, 3, 4, 5, 6, 7, 8. So that looks good to me. And the section here, TV was part of the initial value, so these sections are correct. That's good for me. So this is unpack test row data. Sure, why not? And if we do that, then we have to indent, don't we? So now we gotta be like mutator values. We gotta I really hope, I'm really kind of nervous that I'm going to make some really stupid mistake, like not order these indexes correctly, and then it's going to like be a pain in my ass to figure out what's going on with the test code. So if the test fails and everything looks correct, that's definitely one of the things we'll have to look at, be like, hey, are we unpacking everything correctly? Okay, so we're going to unpack the test data. And let's look at this table. This table is int32s, but what are these? Are these int32s? They are not. They are unsigned 8-bit integers. That's fine. It just means it needs a cast. And as long as nothing's out of range, that'll be fine. So UO8 cast, and UO8 cast, UO8 cast. Want to make sure there's no ambiguity with these casts. So we're assuming that it's going to do this and then the cast, but, you know, what if it doesn't? So, just in case, let's be paranoid. Oh, well, we can't do that. So let's throw this in here. Let's throw this in here. Cool. 6, 7, 8 still have. Okay, so cool. That looks good. The initial values. Okay, so we're gonna put this brush state, but before we load the brush, we want to what are we testing here? Are we testing toggle tile? What are we testing here? Toggle tile. We are testing toggle tile. So it looks like what we're going to do is load the brush. Okay, this is set initial tile value using brush. So we're going to set the initial tile value using the brush. And overwrite tile val So it's important that this is not the toggle section. This is the overwrite. So we should probably like make a note that that is overwrite. Okay, and we're going to use the brush. Okay, so we see these sections here. Seed tile data location with initial value. So this thing actually needs to be the overwrite value. So this TV, this actually needs to be TV. We were correct the first time, so TV initial slash overwrite value. So this is the initial slash overwrite value here. And then we're going to put using the brush. So we're going to put all this stuff that's in the brush. We're going to use it for the put command. So it's going to put this tile value at this quadrant, this exponent, this layer, this x and y local, and this offset index. Right? It's going to do all that stuff, hopefully correctly. Put using the brush. And then after we've done that, we're going to apply the toggle tile. So we're going to run toggle tile. Toggle tile is, we've already set up the brush correctly, right? So the brush state is already set up correctly. However, the brush state isn't quite set up correctly now, is it? Okay, so the TV needs to be swapped to BV. Set the brush value you want to test the toggle tile command with. Right, so it's all the same stuff except this is the different part, right? So a lot of redundancy here. But this is where we're doing the actual toggle tile, but we got to change the brush value. So we should really take a close look and make absolutely sure, because where we're going to screw up definitely is like these things. So these two variables, we need to make sure that they're used in the correct space. So TV is the initial and BV is the brush value. So we know that these are in the correct order already, but we can check again. TV, BV, X expected. Okay, so these are unpacked. They're in the correct order. The initial value here, yep, because it's the, right, we have initial, and then the value we're going to use with toggling the brush. We're going to put using the brush. This put command has already been tested. Then we're going to do a PAINT5D put brush state. We're going to change the brush state. We're going to use all the same variables, except we're going to swap out the initial value for the brush value we want to test with the toggle tile function. Then we're going to get the value. So we're going to say tile value, right? We're going to fetch tile value. Ooh, hold on. This is wrong. Well, first of all, this commentary is wrong, and this is wrong as well. So we want to, we don't want to get the value loaded into the brush. We want to get the value that is on the canvas. So, okay. Get actual value set into bitmap. So we're going to get the actual value that was set into the bitmap, and we're not going to use this. We're actually going to use, I think it's like PAINT5D put is the core function here. Yeah. So PAINT5D get, right? So tile value is what we're getting. So tile value is what we're getting, and act TV is what we want. So we do want act TV It's just that this is the wrong function call. Hopefully we didn't do the wrong function call in too many places. So this is the act TV, and this needs to be a UO8. I don't know if this is a UO8 up here, so let's look at what we got here. So initial values, mutator values, actual values. So we're just using expected. For actual value, we're using I32, but it's not going to be I32. It's going to be UO8. The expected value we can keep as a UO8 as well, I think. I don't know. But the actual definitely needs to be a UO8, because when we're taking the pointer of it, alright, this actual value, this is the, you know, the expected tile value here. We're just going to remove all this commentary and say, you know, expected this is the expected tile value that we expect to be in the data at this location. However, we see that these variables don't exist, do they? This takes UO8s. Are there UO8 versions of these variables? So let's look over here. Okay, so these are our UO8 versions of the variable. So we want to take all of these. Not this, because we want to get the expected value, but we can use all these things again. And then right down here, where we're getting the stuff, we're going to just replace this all with, and also, you know what, let's, no need to get rid of that, right? We can keep those for reference. Instead of 7, we're going to have 6 here, because the syntax, right, we've changed this a bit. We could actually get that. Get expected tile value, right? That has a little bit of room to breathe, where we can kind of tell the difference between that. Yeah, sure. Why not? Why not? Okay. So we'll get the value in the tile map, for lack of a better word, right? Essentially, we're getting a value in the PAINT5D tile map, if we want to think of the high-level abstraction of what's going on. More abstractly explained, get the tile value at this location within the PAINT5D tile map data. But more abstractly, that's what we're talking about. We can also kind of comment that. So say, what time is that? At vid IID. 2 hours, 52 minutes. And 55 seconds. We're going to change that timestamp again because we're taking too long. Okay. 2 hours, 53 minutes, and 20 seconds. More abstractly explained, get the tile value at this location within the PAINT5D tile map data. So we're talking about get the actual value set into the bitmap. Well, each pixel in that bitmap or texture is actually encoding a tile value. So if we want to layer on more abstraction, a more high-level abstraction, then this paragraph describes what we're doing, which is getting the tile value within the PAINT5D tile map data. That's what we're doing here. Okay, so now that we have this expected value, we need to actually check it. And I see we have this actual and expected, and a whole bunch of, like, ridiculousness. that's good. This expected is just, it just needs to change. Yeah, so I'm going to guess that we kind of cut and paste checked against expected outputs. Let's just remove this. So expected here, anything where it says expected, we'll just get rid of that. We'll get rid of this prefix here. Right, it's just called expected in this test. It was called, we cut and paste this from other stuff, that's why it's like that. It's still a tile value, so we can keep the macros like that if we want. So this actual thing, the actual tile value, we call it expected, but we got it, didn't we? Oh, this is expected right here. We're getting it right there. We need another variable, don't we? Mutator value, expected values, actual value. Oh, we have an actual. We already have an actual. It's not used anywhere. And, we need to get the actual value, right? We need the actual value. We were wrong there. Actual value. Let's change the timestamp here so we can see that. Let's do 55 minutes and 40 seconds. Okay. So more abstractly explained, get the tile value at this location within the PAINT5D tile map data. Right, so everything is encoded into a bitmap. So what we're really doing is just getting the value, the pixel value that is set into that bitmap. But if you want to layer on another layer of abstraction, what we're doing is getting the tile value at a specific location within the PAINT5D tile map data. Okay, so we're using the get command, and this is the actual value now. So let's make sure that actual value is used in all the correct places above. Because we didn't know what we were doing earlier, and we kind of screwed that up. So yeah, actual values, the actual tile value, and expected tile value, the brush value, and then this is the initial tile value, right? We got a whole bunch of different tile value variables for all of this, so it's kind of crazy to keep track of all of this. Okay, so that means we just need to track actual versus expected, right? So here's actual and here's expected, right? And where's expected? Expected is kind of taken out of here. Is that a UO8 value or is it not? Expected is a I32. We have a cast right here, though. There's no reason that that expected ever needs to be an int32 with how we're using it. So let's change this to a UO8 value. That makes more sense. And later we may have to change our mind on that. You see that things are not aligned properly. Let's change that, fix that. Cool. So expected and actuals. The expected is here. The actual is not in the test table, right? Because we have to actually get that, right? Tile exponent, not actual. No, we're not going to change that. We might want to make a note. I don't know. That this is not an expected in the sense. This is not exp for expected. It's exp for exponent. That might be important. I don't know. I don't know how I feel about it because now we have two things. Because this is really the delta we want, and now we're kind of giving this more attention. I don't know. It kind of distracts from. This is the thing we really want to do. Well, I guess one way we could make that a little bit less distracting is do a lowercase exp for exponent. Okay, so here's the put brush state. We're loading the brush, we're toggling the tile. Then we're getting the actual value returned as a reference, and the get has a UO8 pointer. Cool. This max tile value. Oh, spam. Nice. So I have a bot watching me. Excellent. This check against expected outputs, tile value, the max tile value, the min tile value. Make sure that the min is less than the max, right? If actual is not equal to expected, we failed the test. We've also failed the test if this happens. This may be a not unique kind of thing anymore. Nope, that's still a unique message. Okay, so we kind of, when we cut and pasted it, we did refactor that. The expected is what we're checking the bounds on, not the... Ooh, hold on. Oh, well, here we're checking them against each other. So the range check, they're already equal to each other if we get to here. So we only have to bounds check one of them. If we want to be a little bit paranoid, we can also check this, right? We can also kind of, if we really want to be paranoid, we can bounds check that as well. In case we decide to put this before that for some reason, we can do that, sure, why not? If we failed the unit test, we want to know the test index, and then we want to know the actual and expected. So actual and expected, and there's no TV at the end of this. It's just actual versus expected. And two of these, because we're printing off two decimal values, or two integer values, whatever you want to call them. And then toggle tile test failed, and then you're done. And then we don't need to say finish test toggle tile. Or do we? Do we need a vital to do? Do we want some more things? Yeah. We want to say, AAC 2020 to-do manager, vital, and say, you know, add more test cases, toggle tile, right? So eventually we want to add more test cases. Right now we're just stubbing in the minimum amount of test cases just to get everything running, but then we have to go back through everything else and then add more test cases. This is gonna suck. Okay, so let's give this a run and see what we got. Number of test elements. Yeah, we never did fill that out, did we? So number of test elements here. If we go back up to the top, checksums. Is the checksum still correct? Looks correct. 9, 8, 7, 6, 5, 4, 3, 2, 1. Yep, so there's 9 things here. There's 3 tests. So we have 3 tests already. This needs to be a 9. We could say 9. And we do write it kind of obtusely, just to make absolutely sure. We know that's supposed to be a 9, that's supposed to be a 3, right? Okay, so let's read through this, make sure that everything's there. So this is a variable declaration section. Okay, sure. Misc test runner vars, sure. Failed unit test, no used variables, test index, max test index, and the base value, cool. These are initial values. The quadrant, exponent, layer, x, y, offset index, and the value, okay. The brush value that we're going to use to mutate the tile value that was initially at that location. The exponent, not the exponent, expected value, right? That's why I made that notation there, because we thought we might get that confused. And the actual, so the expected and actual after using this mutator value, right? So if we look here, so the initial value, the brush value, and what we're going to expect to happen. So if there's a 0 and a 0, and we put a 0, they're the same, so it's technically going to unset the value 0, but that will just lead to 0 being there, so that's fine. Here we have a tile value of 1 and a brush value of 1, so since the tile value 1 already exists there, and we're trying to put a 1, it's going to unset, put a 0. Okay, with a tile value of 1 and a brush value of 0, they are different, so it's going to take this brush value, overwrite this, and turn it into a 0, right? So very basic first test, because we are going to come back to this later. It's going to take us time to get into the headspace, so we don't want super complicated test cases yet until we get all this code running again, right? So we got a lot of ways to go to get this running. Okay, so we're going through all of our test cases. So the test index to the max test index inclusive. The base offset is the test index times the number of test elements, which is the stride. We're going to unpack the test row data. So all of these numbers should be sequential. Cool. In TV, BV exponent, that's the last thing, TV, BV exponent, cool. Overwrite tile value with brush. So we're going to actually load the brush state, which should already be tested, with this initial tile value. Then we're going to put that value using the brush, right? So we created this function just so that we could write this toggle tile code, right? That's the only reason we created this function. It's a helper function for our unit tests. It could be useful later on in the future, but right now that's what it's used for. It's just for testing our functions. So really we should probably make this a private function, but for now, let's not worry about that. That's a detail for later times. Actually, no, let's not do that. We can do it now. Let's do it now. Let's do it now. It's not too hard. So we'll just do TLCMD. So put using brush should be kind of a private function. So private, 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 already private. So this is where we are, right? Overwrite, yeah, this is the overwrite, put using brush. And then in our little documentation thing, same thing, right? So these are kind of, these are helpers for the bound to keyboard stuff. So this put using brush, that should be, this should be lowercase here. So instead of saying void, I don't know where we want to do this. We just want to be like, I don't know, at private like that. Ooh, that might do weird things. Void and at private, sure, why not? I mean, that's kind of weird, but why not? Void and at private, then this thing needs to be lowercase. Okay, put brush state, and then we're gonna like search for put brush state with a case insensitive search and just replace it, right? So, bam, 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 bam. Anywhere that this is referenced, we just want to use the lowercase. That's a lowercase, and then make a note that at private. We could change this. No, we'll just make a public version if we bind it to the keyboard. But right now, this is also not meant to be bound to the keyboard, even though it shouldn't even be used in the first place in any capacity. But we'll make that note as well, because that is the deal. So, this brush state inlined, kind of inlined it twice. Okay, cool. So we made that change. And now that we've kind of inlined this put brush state, right, we were using that. Not here. We're going to use it first in the overwrite, right? So overwrite put brush state, overwrite tile value with brush. So we have to change the brush state, right? So with the TV here, because before when we used put brush state, we used it oh, this is the initial value. This is the initial value. So we have it down further. Yes, we use it again down further with the brush value. So we're going to put using the brush, but we're going to use the this tile value. Okay. And then we're going to make sure that we can correctly toggle the tile. So we're going to reload the brush with all the same coordinates, all the same values here. But then this value is going to be different, right? This is swapped TV, swapped to BV. So now we have the brush value loaded. We're We're going to run the toggle tile and see that that works properly. Okay, so if that works properly, then the next thing we want to do is say, okay, well, did the actual value, do we have the actual value in the data, in the tile map that we expect? So all these same values here, but now use actual here. Then we'll check actual versus expected here and do all that fanciness, and if we failed the unit test, we'll kind of print off what those values are and say that we failed the toggle tile test. So that all looks good. Let's give that a run and see what else we might need to fix. So we're hoping that eventually we're going to get a runtime error. So unused variable, so it's called no use, but I'm sure that what I did was I probably have a no use 1 and 2, but then I didn't use the third. It should be used, but we made a typo. I guarantee there's a typo here. So no use 1, 2, and 3. There they are. We'll hold up here. If they're there, then what's going on? I mean, they're used, are they not? Let's look that at again. That might be on a different, oh, it's in the next function. It's not in this function, right? We cut and pasted a lot of stuff, so in the next function we have, I guarantee that if we look at this, we'll find the problem right away. 1, 2, 3. 1, 2, 3. That sure looks like it's used. Unused variable, no use 3. What do you mean it's not used? It's 4006. Oh wait, we still need to go further. Never mind. False alarm. We cut and pasted so much. So 1, 2, and 3. 1, 2, and 3. 1, 2, and 3. Oh, we're getting closer. So 4006. Here we are. So down here, are we using no use? Actually, we're not using it anywhere, are we? So for toggle tile, we're in the toggle tile code again? We're back in the toggle tile? Yeah? Yeah. Okay, because we're getting the tile, all of our getters are using these kind of higher level getters. Except for this, yeah. We're not using the tau depot functions in here. That's why we don't need the unused variables anymore. Okay, fine. Fine, that's okay. That's okay. We can just nuke these. That's fine. And then give this another run and see what we got. Error, return with a value in function returning void. Okay. So unit test pragmatic controls void. I just want this to be return. Okay, so we're getting further. We're getting further to where I think what I'm gonna do is, oh boy, we're at like 30 of everything right now. 30 push-ups, 30 whatever, 30 jumps on the trampoline, and it's fucking cold. Must back up data for a test. So we see this error. Are we actually doing that now? Because I think we are actually doing that. Yeah, so if we say backup data for tests, that's true. We do need to do that. But let's remove all our Control-Shift F4 for a second. Actually, no, let's actually go through every single other breakpoint and make sure it's not kind of important. So let's go F2. Whatever, don't care. Okay, don't care. Actual global TX, actual global, sure. Okay, don't care. The table of unit test code, that's kind of scary that we don't have any constants here. Because we have a 9 times 2. So I get it, there's a checksum 9 and 9 times 2. Okay. Times the number of columns. Oh, there's 2 columns here? 1, 2, times 2. Okay, yep, that's right. It's kind of when I don't have defines for things like that, it scares me, though. Ooh, why is there a whole thing here for cell instead of offset? Sure, we can delete that later, but let's not delete that until this code actually runs, so we'll keep that there for now. some craziness from a few days ago, I think. So let's remove that. Calc, rebase, whatever, don't care. Don't care. Old stuff. Old stuff. Don't care. And the reason why I'm doing this, instead of just clearing all of them, is bx, by, bx, by. And the reason why I'm doing this one at a time like this is because just in case there's any other important considerations that I may have bookmarked to say I need to come back to this, right? So expected bx, expected by, min and max comparisons. This is bx, by, xy, the minimums. bx, by, maximums. Okay, that's fine. That looks... This is just spot checking. We're not getting too deep input using brush. We're getting to the code we just wrote. Okay, so now we only have this one breakpoint here. That's cool. And yeah, we do need to back up the data for the test. I think that we're already doing that, though. So we need to look for the word backup. Because I bet... yeah, we have a system data backup. And before we call these unit tests, we're backing up the tau-dirt. We're backing up tau depot, and we're backing up PAINT5D. And we actually have a problem here, because we're in PAINT5D, right? Oh, actually, no. We're not. We don't have a problem, do we? Actually, we kind of have a problem, don't we? Okay, so let's look at how we organize this code for a second. Pixback. So where is Pixback? So we have a problem. Pixback is right here, but we have a thing called some of these are referencing the future, and it's okay, except this one. That's not cool because it's yeah, backing up tau-dirt. We can't be putting it in there like that. It violates the Pixback is forward referencing tau-dirt in here. These ones are okay because they don't reference the systems. They actually reference the pix name allocations, which is okay. So that's okay, but this one is not okay. So we need to make a note of let's make a note of this in our agenda here. Properties. Is that locked? Okay, let's edit these. So So 06 is now an invalid So this is a big mistake. We're gonna have to fix that eventually because we're wrecking our library chain. Oh wait, check every part of library, compile all variations Okay, right, so we have some more things we want to do. Now our agenda is kind of getting large, so we're gonna have to kind of make this smaller. Okay, you know what? We're just gonna let... That's way too long. We're not gonna worry about it right now. We'll just keep this kind of big, and we will... Because the note is there. It's okay. It's like a mystery note right now. Is invalid back, something or other. Compile all variations of libchan to check for backwards, something, something. We're not going to worry that some of these to-dos are off the screen, because these aren't the to-dos we're concerning ourselves with at the moment, so it's fine if we don't know exactly what they are, right? That's fine. Okay, so let's keep on going here. Well, yeah, but we do need to address that, because it is a mistake. So let's do like a... Make a note here as well. Tau dirt backup is invalid back reference. Fix. Alright, so we need to change the organization of our code if we're going to abide by that library chain structure. I do like that all the backup stuff is consolidated in one place. If we really want to have a correct forward reference, we could do some weird stuff with our memory allocations. No, we don't want to do that. We could do some weird stuff to make it okay, but let's not do that weird stuff. Let's, if the code seems a little bit awkward, but everything's easy to find, that's better than it being less awkward, but things being harder to find. So, okay. So let's keep on running this until we can finally get it to start compiling. And yeah, this must backup for test. We already see the system data backup here. Then we're running the test, the pragmatic controls, the test controls, the user controls. So all that's fine actually. We already have, the stuff is backed up. We kind of check that code to make sure it's there. So now we're gonna just remove these errors. Because we put them there because we were scared that we forgot about it, so we just kind of put them in our git put tests. So I think we just put it where we thought about it. We just kind of like shoved it somewhere, it looks like, because UTC put, this is a very specific test, is it not? So UTC put, let's kind of look at this for a second. So what is this? I'm going to guess this stands for put or get. Okay, so we're going to have a double loop. It looks like we're going to have the test index and a put and get. The base offset of test data and the number of whatever. So we probably have two test tables, don't we? Yeah, number of test cases put. And then we have another test table with... okay. Okay, hold on here. We have a PG. Okay, let's highlight some things that kind of stand out here. Put get. We have this put get thing. Is that anywhere? Yeah, so put get equals... Oh, okay, so we want to get exactly what we put. That's why there's only one test table, because we're going to put all this stuff, and then we'll use the same exact test table to get it, right? And we're going to run we're going to run through the entire table. And we're going to put everything before we get everything. Yeah, and we've kind of explained that before. We've kind of gone through this code before. Okay, that checks out. I'm fine. And let's, since we're here, why don't we make this a little bit more detailed? More tests. And then this thing, right? So this is the test code. So just say, hey, more tests of this thing, right? And this should also be between brackets because it's a hard-coded string. Okay. Let's see what else we got. Let's see what other mistakes we have. This is painstakingly painful. UTC put. Tile value undeclared first use in this function. So tile value. Okay, so that's great. So we have a value that doesn't even exist in our code. And that's bad. So let's so we have all this stuff, and it happened at tile value. So for whatever reason, we call this put tile value. Why are we calling this put tile value? Why are we calling this put tile value? Because it's not just it's the expected and actual, is it not? No, we have a put tile value and a got tile value, right? So we're gonna are we gonna extract it first? Depending on the loop, are we gonna set it to something different? Oh no, got tile value we use this way. Right, we actually get it. That makes sense. Okay. And where is the tile value that it's let's highlight this as purple for a second. I think the number 4 for that. And there's a section here where we're just referencing tile value. Okay, so we're checking for integer overflow here. Number 6, so yeah, so we just want to call this put tile value. If we really want to avoid problems, we could just say tile value like that. And because I'm just sick of this, so we could do define, and it is the put tile value. And then we can just, you know, undef. And that way we don't wreck our formatting, right? We can keep our nice little formatting here without kind of screwing it up, right? It's kind of ugly and hackish. We might want to do this, like, you know, throw this here like that. It's ugly. It's very ugly, but it'll do, right? And I think that's the only place we're referencing it. Yeah, that's the only place we're referencing it, so yeah. Okay, let's run this again, see where else we screwed up. Void AAC 2020 PAINT5D UTC gets ISO C prefer nested something or others. Oh boy, so on 44,000 we have not 44,000, geez. We have somewhere in our code at this point in time, we have forgotten to close off a multi-line comment. And to figure that out, since we usually do double stars, we can probably easily find it by just going highlight the opens and closes, and just look for a point at which, looks like we did this as well, so we'll have to do this. Highlight those opens and closes and just see, is there any point at which this is not lining up? Or are we doing anything tricky somewhere? It looks like we're pretty good with this. Doesn't look like anything's... So let's run this again and see kind of what line it's on. So 44,434. It might actually be kind of further down. 4,434. So it's this guy here, right? Nested function. Well, it's talking about nested functions. So that sounds like we didn't close off this function correctly. And if we think about this, we have a double loop here, don't we? In this code here, there's a double loop. Is there not? Yeah, because if PG equals this or that, and where's our double loop? So here's our double loop. And if we have a double loop, then down here we need to close it off twice. And we kind of... Yeah, so I see what we did here. Close it off, close it off. This is next. The outer loop is the put get, and the inner loop is the the test index, and then this is the actual function here. And this is the end of the function. Yeah, we're not even going to denote that. If we really want to, I guess we could Let's take off one of the namespaces so that it helps as a reminder of what we're doing, but, right, and, right, we can do that, sure, why not, because things are getting a little bit long, so that can help us. Okay, let's see what else we kind of messed up here. Oh, yes, and if we're doing this, we cannot do that double semicolon thing we do. Well, that would be a mistake. So, you know, originally when we were tying up those loose ends, we kind of, like, spammed stuff all over the place because, test all the values on the 512 by 512 bitmap. So we have a blah, 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 and did we finish this code? I mean, if we had this blah, 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 that is kind of a cue to me to be like, maybe we did not, oh god, we're gonna have to do 40 push-ups, 40 whatevers, because this is almost at 4 hours and we haven't done any of that exercise. 40 is a little bit too much for me, but here we are at this time, so let's get this done, because we're actually going to go out on the trampoline and do 40 jumps as well, so and then we'll kind of get to this stuff here. Not finished, is it? I don't know. Okay, so we'll get to this stuff here, because I don't know if this test function is finished. Judging by the smattering of stuff here, that's a cue to me to say, maybe this is not finished. So we're going to have to look at it again. But we'll do 40 push-ups and 40 etceteras, and then we're actually going to go out, jump on the trampoline, do 40 jumps in the freezing cold, because, man, we saw ourselves in the camera today, and holy... We're just getting super pudgy. We're like 30 pounds overweight here. We gotta fix that problem before it gets way out of hand, right? So 30 pounds is already too much. So the drugs I'm on said they would make me kind of gain weight, but just fuck this. We're gonna do what we can do to stop that. So push-ups. So we haven't done any today. So let's do 40, and then 40 of everything, then crunches, squats, dumbbells, etc., and then go out on that trampoline and jump, and then we'll be back. So I have no clue how long this is going to take. So actually, since we have no clue how long this is going to take, it would kind of make sense to have a timer, right? So it makes sense to have instead of a countdown timer, it would kind of make sense to have some type of timer. So let's add to our push-up screen, let's add another display capture and create new push-up red timer. We'll call it push-up red timer. And if we have this, can we just throw it? Right now, we could kind of actually just throw it in the background, could we not? Or is that not a thing? Let's try that, so, okay. Oh boy, that is, no, we can't do that. We gotta crop this, so let's crop this. Properties. No. We need a filter here. So filters, we're gonna add a crop. And then we're just going to say, I don't know, 222. We're just going to add 222s everywhere. And then we're going to fix it as we go. So how about 200? That's a little bit too much. How about 190? That looks pretty good. Now the bottom, 222. How about 444? How about 555? Too much. How about 520? How about 500? That's pretty good. How about the right? How about 333? How about 340? Okay, and the left, how about 340 as well? That's good enough for me. Actually, it's not good enough for me, is it? So the top, let's do a 195, just to kind of, yeah, that looks a little bit more centered, because we might want to center this graphic, so we might as well crop it in a centered manner. So let's close this, and now we have this little timer, and we'll just kind of keep it up here, just to make a like I don't know where we want it, but yeah, because I have now that we have kind of stuff here, I want to have a kind of an idea of like how long is all this going to take. Just out of curiosity, because we're starting to stack a whole bunch of stuff here, so we're going to do 40 of everything, and then we're going to run outside and do 40 jumps on the trampoline. Probably have to clear it off, run in the snow, get really cold. I don't think we'll get frostbite. I think that it's not that cold, and we're not going to be out there for that long. The idea is just to get get more cardio is basically what I need. So, also chaining together more exercises, more time with the elevated heart rate, right? So, okay, so that's good. Let's start doing everything, and we'll be back whenever I'm done. I have no clue when I'll be done. One, two, three, four, five, six, seven, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 10, 11, 17, 18, 19, 20. Okay, dumbbells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay. 20 more of everything. 1, 2, 3, 4, 5, 6, 7, 8, 9. God damn it. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. Crunches. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. Squats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 15, 16, 17, 18, 19, 20, okay. Dumbbells, and then outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 18 again, 19, 20, and then 20 again just for good measure, 21 and 22. Okay, we're good. We've done. Right, so now we gotta go outside. So we're at 5 minutes. Whew. Okay, so we did 40 of everything. It took us less than 10 minutes to do that. We did really crappy jumps on the trampoline. It's frozen over. I was barefoot. I need to clean that off. But let's keep this do or die kind of thing with the exercise. Okay, cool. So let's get rid of that. Let's go back to the bottom monitor. And I might want to actually take a break to make some food. See, that's the problem. You do that exercise and then you're like, man, you know what? Now I need food. But I need the food. I also need to go to the bathroom and whatnot. So let's do an actual break. My pork chop already is defrosted, so let's not worry about being overkill here. You know, if we want a 30-minute break, let's have a 30-minute break. Have some time to start our food, empty our bladder, come back downstairs. Right? You can't always get pure work in. You also need times to give yourself a break. So let's do that. And I want to stop coding once I get everything compiling again. Is probably when I want to stop coding. I don't know. Let's reset this to 32 because I'm obviously talking. Let's give it 35. Let's give it 35. Okay, see ya. I'll be back.
Okay, so I'm waiting for all the YouTube commenters out there to start telling me why this is absolutely okay. There's no real problems here. Intel looking at outsourcing its CPU manufacturing is completely fine. It is completely fine. Nothing to see here. Intel getting out of the chip manufacturing business, that's not really a significant problem. The funny thing that I find is, again, I've been in tech since 1996. What are we at? Is that 24, 25 years at this point? I don't know. One of the interesting things that I find is over those decades, right? We have businesses that come out of absolutely nowhere. They take over an entire market, and then after a certain point, they die. But the interesting thing is, in the process of dying, you have all these commentators and pundits that come out of the woodwork to explain that what is happening to these corporations is not death, really isn't a problem. It's like, no, 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 they're completely fine. You just are not smart enough to understand what their business is. And then, like 5 years later, they go bankrupt. And then the pundits are off to explain why some other failing business isn't actually failing. I remember Sun Microsystems. I remember AOL. I remember BlackBerry and Yahoo and MySpace and Groupon and all these different companies. I remember when they came out of nowhere. I remember when they took over the entire market. And then I remember, again, the interesting part is when people were arguing about when they were going into their death spiral, how that wasn't really a death spiral. They were just gaining speed. They were just gaining speed so that they could fly even higher into the future. And then they died. So Intel has been an interesting corporation over the past few years because Intel has been a premier company for a long time. Basically, for my life, as long as I have been a sentient human being or whatever, Intel has been around doing some pretty cool things all the way from the 286 era. My family literally had a 286 computer to the 386s, the 486s, the 586s, all the way up until about 2015. Intel was really just an amazing manufacturer, creator, and manufacturer of processors and CPUs, and they seemed like they would always have market dominance. Like there would be AMD, right? AMD is a direct competitor to Intel, but I don't know. It's kind of saying like the local hamburger joint is competing with McDonald's. I mean, to a degree, yes. To a degree, yes. Like the local or the regional hamburger joint may be able to steal a couple of dollars from McDonald's pockets, but at the end of the day, McDonald's is always going to win, or it seems like it's always going to win. Again, ARM comes out. ARM is like a different food. Maybe it's the I don't know, it's the Baja Fresh or whatever of the processor world. And again, it takes its little market share, it has its little niche, but the idea is McDonald's is just still going to dominate. But at a certain point with Intel, ARM processors kept getting better and better and better and better. AMD processors kept getting better and better and better and better. And Intel processors, you know. They're still there. I mean, I guess they're better. I mean, like let's be clear. Let's be clear. You can't say that a processor in 2021 is worse than a processor in 2015, but it's not. It's not what we were expecting. Over the past 5 years, Intel has just lost its leadership in the processor game, regardless of what the commentators out there say. And literally, it now looks like it has gotten so bad that they're actually thinking about outsourcing the actual processing manufacturing, which is just that's just scary on a whole bunch of fronts. So we go over, take a look at Ars Technica. So a lot of different places are talking about this. But an activist hedge fund basically has purchased a lot of Intel shares. And so what activist hedge funds do is they buy shares in companies where they think that the company has more value. Basically, if management would actually like modernize and do things in a better way. And so what they do is they buy a lot of shares in a company and then try to force that company to become more efficient or spin things off or whatever else, and then they sell their shares when the value of that stock goes up. So this activist hedge fund is coming in. They're basically looking at Intel, and they're just being honest. They're saying, look, Intel is resting on its laurels. Intel is no longer the preeminent, processor company that it used to be. It is going downhill. So we want Intel to start doing things to bring back more profitability to the company. And it looks like outsourcing the CPU manufacturing might be one of the things that's really on the table. So Activist Hedge Fund advises Intel to outsource CPU manufacturing. Third Point, a fund led by Daniel Loeb, demands strategy shakeup. Activist Hedge Fund, Third Point, has taken a stake of nearly $1 billion in Intel and called on the chipmaker to consider shedding its manufacturing operations, throwing a core part of its strategy into question. The firm with $15 billion in assets, run by Daniel Loeb, made a number of demands in a letter sent to Intel's chairman Omar Ishrak on Tuesday and seen by the Financial Times. In the letter, Mr. Loeb said that Intel was quote, once the gold standard for innovation or innovative microprocessor manufacturing, but had fallen behind manufacturing competitors in East Asia such as TSMC and Samsung. His intervention comes as Intel faces a critical decision over its future as a leading-edge manufacturer of semiconductors, a position it has held for decades and the source of its dominance in the PC era. Bob Swan, its chief executive, has indicated that he will decide early next year whether Intel should outsource a significant part of its most advanced manufacturing or even get out of leading-edge production altogether after a series of slips. Think about that. Think about a company like Intel saying that they're going to get out of leading edge production and manufacturing. Think about that even being on the table. Because when they say it's on the table, it most likely will happen. Because this is something that is so significant and is so dramatic and is just such a world-shaking type thing to bring up that you don't bring it up unless there's a good chance it'll happen. And so the fact that they're talking about outsourcing a significant part of its most advanced manufacturing, that is just a bad sign. The company in July revealed it had hit a new hurdle in trying to move to the next generation of manufacturing technology, where the features on chips are reduced to a width of only 7 nanometers. That compounded a series of missteps that helped cement the lead seized by TSMC, the Taiwanese chip company that manufactures semiconductors on behalf of many of the world's biggest chip designers, including NVIDIA, Qualcomm, and AMD. So it looks like Intel is going to start throwing in the towel, and it's one of its main things that it's known for. And the question is after they do that, at what point is the game up? I mean, once Intel starts handing over their advanced manufacturing essentially to another company, at what point is Intel basically in that death spiral, right? There's this idea, well, they'll still come up with intellectual property or whatever else. But I mean, Intel's significant. They came up with the property. They actually did the manufacturing. They were at the leading edge. And so for them to slip so far behind that they're talking about giving up a huge chunk of their manufacturing just really brings into question what the value of Intel is going forward and what happens in the future. Again, there's an interesting question as far as the national security concern, right? Having Intel actually create the processors, an American company actually creating the processors, that's a useful thing. What happens when all processor manufacturing is done in Asia? That's going to be a hell of a thing. How do you get into a trade war with countries or get into trade negotiations when those countries are the ones that are producing all of your CPUs? That's a hell of a, I mean, you think about it in the modern world. The CPU is essentially the water of the modern world. What happens when you get into a spat with countries? What happens when you have issues and essentially they have the equivalent of digital water? How does that work out? One of the more interesting things is, again, when you start talking about China trying to rise in military prominence in the world. What happens when TSMC, right? They have their manufacturing plants in Taiwan. What happens if China decides to bomb those things? I'm not really worried about China bombing the U.S. For China to bomb factories in the U.S., things would have to escalate to a horrendous degree to get that far. By the time China is bombing factories in the U.S., we're well past World War III at that point. But again, with Taiwan, you got the whole issues between Taiwan and China and one China policy and everything else. There is an interesting question of like, what if a couple of bombs accidentally drop on the TSMC manufacturing facilities, and then what does that mean for the U.S. if manufacturing of chips has been basically outsourced over into Asia? I think it's a lot of interesting questions there, and so I would argue short Intel. I would argue short Intel. I think Intel's going downhill. Again, you've got Apple, they're moving over to ARM processors. You have Microsoft coming out. Microsoft is talking about producing basically their own data center ARM processors and possibly moving more of the PCs over to the ARM processor format. What we've learned is again with everything from smartphones to tablets to smart TVs, ARM processors at this point are doing the tasks that most of us need to get done. And so I think there's become a real question about how valuable Intel products really were. At one point the brand of Intel held enough premium to it, as I used to say. I used to always sell my clients Intel processors, right? So the difference between when you go back to 2010 or before, the difference between Intel processors and AMD processors was usually horseshoes and hand grenades. They would basically go back and forth, right? So Intel would do something, then AMD would come up with a slightly better processor that was less expensive than Intel, and then Intel would come out with a better processor, then AMD would come out with a processor, and Intel would come out with a processor, and AMD. But one of the reasons that I sold Intel processors is because back at that time, the naming convention made a hell of a lot more sense, right? This is a P4 with a 2 gigahertz processor. This is a P4 with a 3 gigahertz processor. This is a P4 with a 1.5 gigahertz processor. It was a hell of a lot easier to have people think they knew what that meant. They didn't really know what that meant, but to have them think they knew what that meant versus AMD had Semprons and Optitrons and sounded like the Transformers had a naming party in order to come up with their names. And the problem was, again, when you're actually selling to customers, if you can say, okay, you're going to spend, I don't know, $600 on a P4 1.5 gigahertz processor, or you're going to spend $1,000 on a P4 3 gigahertz processor, right? That's a lot easier for people to rationalize a price difference. When you're talking about Semprons and Optitron, nobody knew what the hell that meant. So it's just like, I'll sell Intel. All right, a couple of bucks, doesn't really matter. What I think is interesting now as we go into 2020, again, AMD has come out and like their prices are just so much lower. They're so much lower than Intel's, and so the price to performance on some of these Intel processor, it just beats the crap out of Intel. And then it's, again with ARM, all these ARM devices are coming out that are doing the tasks surprisingly well, and so I think there really does start to become that question of not only you have to ask, does Intel have a price premium for their brand, but is Intel even really the leader that you care about? Again, when we talk about processors, an important thing to understand, again, with all technology, is for a long time, like being in the leader really matters, right? So if Intel has a 300 megahertz processor and AMD has a 200 megahertz processor, the difference between those two things is massive. It's whatever 33% better, right? So an Intel processor is going to be a lot faster than an AMD processor. The problem you run into though is, again, like with, let's say once you get up to let's just say 3 gigahertz. If Intel has a 3.3 gigahertz processor and AMD, let's say, has a 3 gigahertz processor, does that difference actually matter? Right? Okay, it's 300 megahertz difference, but from a practicality standpoint, does anybody care? It's like with the Raspberry Pi. So I got this Raspberry Pi over here I've been working with for my projects, right? So the Raspberry Pi, this is a Raspberry Pi. It's a 4B, so it has whatever the AMD processor is, the whole 9 yards. It costs about $45. So this thing is about $45. I'm using it for my projects. One of the interesting things about it is how well it works. How well it works. At one point, I didn't even get the special version. I actually installed Ubuntu, the server operating system, and then I upgraded to the desktop operating system using the Raspberry Pi. And I did that for one of my classes just to show that it could be done. Like if for some reason you need a graphical user interface, you can get a graphical user interface and with Ubuntu on the Raspberry Pi 4B. What I was surprised about, and honestly, I did not expect, was that it ran well. It ran well. Everything other than YouTube. Like YouTube was like quirky, but like if you want to do almost anything other than YouTube, it actually ran surprisingly well. And with YouTube, I think it was more driver type issues than anything else. The processor was fine, the RAM was fine, the IOPS, the storage speed was fine. It worked really well. And so again, that's one of the things like you start running into the problems with Intel. Even if Intel comes out with the greatest next Xeon processor that costs $10,000 or whatever, when people are looking at $45 Raspberry Pis, and again in the modern world of computing, if you're like, well, look, I can buy a Raspberry Pi for 45 bucks. Let's say $100 all in with the micro SD card and the power supply and all that, and then I can create a cluster of 20 Raspberry Pis in order to do like distributed workflows or whatever. At what point does that become a much better value proposition than one, monolithic, $10,000 Xeon server? And I think that's the problem that Intel is going to be running into. Again, like when you look at, again, so many of the ARM processors nowadays, are they necessarily in some ways better than, the i9s or whatever? No. But for most people at this point, if it's like, okay, you can buy the latest i9 processor for $1,000, or you can buy a good ARM processor for 50 bucks. And they're like, okay, well, what is that ARM processor going to do? It's like, well, it's going to do word processing. It's going to do YouTube for you. It's going to do video editing for you. It's going to do all of these tasks. At a certain point, people are like, okay, so I can get that for $950 less. I'll take that one, right? And it's only gonna get worse from here, right?
Uh, okay, so I was just on my break searching for, is the C language dead down here? And and the reason I'm doing this is just to compare notes compared to what happened when Flash was dying, right? And see what that looks like. I also do like, is OpenCL dead? And kind of read about it and see like where your confidence is with this language. I was already pretty confident that it's going to be around forever. That hasn't really changed my mind looking this up. I do think that if you have to seriously look up is C dead, like you're seriously concerned, that could be a bad sign. That could be a sign to stay away from that language. But I don't know. I mean, maybe that depends on your level of experience. With my level of experience, yeah, if I have to seriously search, hey, is this language dying? Is this language dead? If I'm seriously searching for that because I'm seriously concerned, then that would be dangerous. That would be like, I should probably stay away from this language. But I'm not seriously searching here. I'm just like, I want to compare notes to somebody searching for, is something dead that I know that's alive versus something that's was dead that I knew was dying back when I searched for, is Flash dead, and kind of get a feel for what the signs are for a language that's still alive versus a language that is dead based on like the chatter around it, Can you name any non-trivial C software that never had any buffer overflow vulnerabilities? Can you name any non-trivial JavaScript software that never had any buffer flow overflow vulnerabilities? Like, it's ridiculous to risk taking down a whole OS when all you need is to parse 200-byte string, Blaster and Sasser. It's ridiculous. that reading of simple data structures is a notorious source of critical security bugs. Every OS X security bulletin contains a couple of overflow in reader for image format X. Makes sense. But imagine making a reader in a high-level language. Think about how slow that's going to be. Whether it's the fault of the language or programmers, the odds are pretty much against security in C. C should be used as an assembler is today for tightest performance critical loops and hacks. Compared to ASM, C is a blunt tool. It's not supposed to let you write self-modifying code or manipulate stack frames. Yeah. There may well be a non-trivial C application that hasn't had a bufferflow overflow vulnerability ever. I certainly wouldn't rule it out. It would be foolish to say all C applications are insecure. Yes, it requires better programmers to be stable and secure, but the gains of doing things in C, or for that matter C++ or Objective-C, are to the user. The application is faster and uses less memory. C days are not numbered. It is often already the case, only that whole application isn't written in C, C++, Objective-C. The libs are C and the rest Python or something, gluing it all together into an application. But even then, an application that is all C or C++ is generally noticeably faster / slimmer. It's of course a sliding scale of development time. What the programmers know, features, and the speed, slimness of the application needs, many users will even take less features for sake of speed or reduced memory use. Assembly isn't going anywhere either. The compiler and language aren't always going to be up to date with the instruction set. If you're writing a compiler, including just-in-time compilers, which means also virtual machines too, you'll always need to know assembly for the target platform, even if you aren't writing assembly. It helps to be able to read it, to see how your code has compiled, or to debug through to the call to the function you are interested. If anything, ASM in some form is going to outlast C. So I would believe that. The lower level you go, the more longevity a language has, because the more things that rely on it. It's easier to make a new programming language than it is to make new programmers. Well, that is true. Okay. LOL recruiters. Thank you for learning C. I would hire you for any programming language job, that is all. But do they hire people? She's looking out for herself as she gets paid to get people jobs, and selling you on C could be a hard sell, as many developers in her market could be GUI business applications and internal applications. C# is probably the most in-demand flavor of C. So when they mean higher level, they're actually talking in semitones. Wow, never knew. More work being done in higher level languages and less in low level ones. A consequence of Moore's law and multicore, yes. There is a disconnect between features C provides and the needs of 90% of all business programming. It's not the same as C dying. And a lot of stuff. Embedded space. C actually isn't as fast as it could due to aliasing problem. Compilers must be conservative in optimizations of pointer access when there are two pointers in a function that could possibly point to the same area in memory. This is what the restrict keyword is for right here. There are ways to address the aliasing problem. C99 includes the restrict keyword for that purpose, and even non-C99 compilers like Microsoft have compiler options to assume no aliasing. So times aliasing exactly what you want. Aliasing is just accessing the same data from multiple addresses. That's not right. Same variable from... Yeah, that's not... Well, I guess a pointer has to be stored in an address. Yeah, I guess that's true. Depends on how you look at it. So you have two pointers that point to the same memory address. They're saying multiple addresses, but those pointers themselves have to be stored in a memory address, right? Everything exists somewhere in a memory address, so I guess technically that's true. Interesting. Pretty sure that is not a random number. I'm pretty sure that's the maximum value of a 16-bit integer. Yep. That's cute. Let's let's see, when were they last on? 11 years. Can we message them? 2 points 3 years ago. Alright. How do we message them? I thought there was a way to do that. Oh, here we go. Alright. We're done here. Yeah, so we gotta see if this code actually, is finished, right? So, it's a put get test. We're gonna put stuff and then we're gonna get it, right? So, it's our test that's gonna test, like, everything in one big go and test like every single coordinate, right? Put get, right? We call it put get because we have to put before we get. The XY location, this is the global XY location on the buffer, which is 512 by 512, so that's why it needs to be an int 16 to do all of the addressing. We have some variables. Okay, so here's px and py, and then we use them. Global tx and global ty, sure. So we're going to convert the global pixels to paint pixels, and these are the paint pixels right here. These conceptually make up a paint pixels object. Then we're going to take the paint pixels and convert them back to global pixels, and this is global 2, and then we'll check global 1 against global 2, right? And then, if that fails, we'll say that it failed. Yeah, so that actually looks pretty solid. Now, I don't know if there's any, like, mistakes or whatnot in the code, but, in terms of syntax or whatnot, but this looks pretty solid in terms of doing what it needs to do on the tin. So I would say we can delete this. This is what it does. About this test every single possible value there is by iterating over the entire 512 by 512 bitmap in a double nested px py loop. And also, hold on. So what we really should do here, we shouldn't, oh, so these are the conversion functions, and therefore we don't have to, like, do all of one and then all of the other. Because these are conversion functions and not, well, hold on, put get. Oh, I see. So this code is definitely not finished, actually. So, what we're doing here is, it looks to me like we're gonna run the putter and the getter. We're gonna run the actual underlying conversion function, and we're gonna test that first. So before testing get and put functions, we will test the underlying conversion functions first. Okay, so these underlying conversion functions don't need to do all of the all of this and then all of this. They can do this and then immediately that, because they're not storing any data. Now, the next set of tests, right, we're going to copy all of this and do it all over again, but we're going to use a PG for put and get. And do we have something similar over here? Like, what's going on over here? Do we have a PG? It doesn't look like we do. But yeah, so in here, on the outside, for PG equals 0, PG is less than or equal to 1. 0 to 1. And PG plus plus. Is that right? So this is triply nested. And we are testing... It says testing the put get, so I assume that what we're testing is this thing here. All right, we're testing this, but we're testing the whole thing. Yep, so... we're in PAINT5D, so actually we're not testing this. We are testing... Let's look at our notes. So here's this put. So what we're doing is we're going to... all these conversion functions, we tested to make sure that they... Let me think about this. Nope. If we do all the putters before we do the getters, and we auto-generate the values, that'll avoid pigeonholing us, won't that? So, we want to do if 0 equals PG, then this is the put test. Else, if 1 equals PG, we've done this somewhere else, but now we're just doing it here. So else, okay. So we can kind of throw this in here, and we need to get these values, don't we? Okay, so we have tile, quadrant, and all this stuff. We got all those guys already. We might want to make sure. So for the put, the offset dex and the tile value, though. Yeah, because that's a different conversion value. So for the so we gotta loop through even more stuff. So we need every combination of this, but then we also need every combination of the os dex. So so let's kind of add a little bit of extra nesting here. So for os is less than or equal to 15, or we could say that, we could call it 16 minus 1, if we want to know kind of how that value was arrived at, give a little bit of insight about that. And then also this tile value. So, we have a tile value already, right? We have, oh no, we have this global whatever the heck. We don't have that, so, so we're gonna say, the value is going to be between 0 and 3, because there's only 4 bits. So 0, 0, 0, and then 1 and a 0 and a 1, and a 1, 1. So this loop in here, so we're gonna have double double, and then this, like this. So this is PG here. Then over here, this next thing is os and val. And this thing in the innermost thing is our px, py. Okay, so we got all that looping. We got all the okay, so now we have this very huge nested loop, and os dex and tile value. Right, we're gonna change that to like os. And we can make a note that that's osdex. And then the val, this val here. Do you have enough room to indent again? Actually, we do. One pet. Put everything, then get everything. So this is what is going on in this section. We're gonna put everything, and then we're gonna get everything. And so we got this just huge n by n kind of gigantic loop. Put everything, then get everything. And we might as well say, you know, UO8 PG. UO8 os. Okay. UO8 val. Alright, so these are just the new variables we're introducing. The px and py already existed. But we'll just kind of declare, so put or get. Okay, this one is offset index 0 to 15. This here is tile value 0, 1, 2, or 3, right? Because we have those 4 possible combinations, because we only have 2 bits, 2, 4. Okay. So that looks good to me. It's for the put. And this value here, though, what are we doing for the value? We're just kind of looping through everything. We actually don't want... The value itself needs to be... we want to loop through every single value, because we're just going to end up overwriting it if we do that. So let's remove this value part of the loop. And in here, we're just going to say val. We're going to remove that. And, you know, why don't we just kind of double loop it with os and pg, right? So os, pg, and then os. You know, why not? So pg and os. Oh, and this is another double loop. So we got 2 double loops right next to each other. How are we going to generate the value? So I think that inside of here, val equals 0. We're going to reset, before we do the next get put pass, we're going to reset the value to be equal to 0. And then what we can do is we can say that the, we can do equals, val equals val plus 7. We're going to create a generator for generating the value to get some more interesting values. So we'll call this valgen, and then valgen is what's going to get reset. So we'll reset valgen right in the middle, and then valgen equals valgen plus 7. And let's actually use a U32 for this. So I have like a lot of room for this. And we still need val, but then val is going to equal val gen modulus 4, right? So it's not going to include 4. It's going to, once it hits 4, it wraps around to 0. So 0, 1, 0, 1, 2, and 3. Okay. And then after we've modulated it to where we want it, we're going to say, oh, you're U8 now, cast that to U8, and then we're done there, right? And then we'll assert that, val is less than or equal to 3, right? And the reason for that is, this is the, max tile value is 3. That's why we have that kind of hard-coded there. Max tile val is 3. And then we gotta close that off. Okay, so we have a little assert to make sure we don't screw that up. We'll have this generator, and the generator is going to be reset for the next series of put and gets, right? So we'll regenerate the same series of kind of pseudo-random numbers and make sure that it all works. So here's our put, and then we want to run the same exact code for the get. And the put function does not have any pointers, but when we use it as when we use the get function, I believe it's the output is the tile value, right? So on this val, we're going to say at, because we're auto-generating val again, we want to name this got val. Or actual value, whatever. We'll do U08 got val. And if we're going to do that, we might as well say that val is, you know, put val. Might as well call it put val, right? It's tile value slash put val. I don't feel like renaming it. Let's just call it val. And over here, got val. And else, this is an error. PG is out of bounds. And then down here, we're just going to, you know, if 0 or, well, I guess we don't really need to do that. If got val is not equal to val, then we're going to say that the test failed. Okay, there's one other thing we want to do. We want to make absolutely sure that all these things got hit. So if we loop through everything, loop through set all ones. We're going to loop through and set all ones, and then we're going to loop through and set all zeros. And that's just going to give us a little bit more certainty that we actually covered everything, that the conversion functions are actually hitting every single thing, right? And if it's not, then we have a problem, right? Because the conversion should hit everything, except for the very last pixel. Very last pixel, everything but bottom right pixel should end up a 1-bit, right? And then over in this section, everything should end up a 0-bit, except for the bottom right pixel. We can't be sure about what the bottom right is going to be. Okay, so we got this get, we got the put. So how are we going to do this? So we're going to take all this stuff here, px, py, the os, and the pg. Actually, no, we only need these three this time. We're going to take these, and we can just do os, px, py. And we only need the put function. Okay. And we're also going to need the conversion functions, are we not? Yeah, we're going to need... Like, we need to actually figure out, hey, what are these? And also, we did not use them... So we have the put and the gets, but in order to get this, to figure out what to put or get, the coordinate, see, px and py, we're not using it. We actually need to use px and py here. So, global pix to pane pix is what we need to use. So we need to steal this from here. And, right here, we can kind of throw this in. So, bam, right there. Indent it properly. And this is the global, right? So, this is px, and this is py. And everything else we are kind of setting, right? So we're going to set this, set that, set that, set that, set that, and then these are defined within the loop. That's okay. Okay, so now that's actually good. That's good. So global tile x, global tile y. That is kind of what we want. Okay, cool. And it's all nicely lined up. So glock pix to pane pix, global pix to paint pixels. Excellent. Okay, so now the next thing is, for this thing here, we want to use this. So we got to use the take the px py and figure out what we're doing. So all these values we're going to set using the px and the py, and then we're going to put those values that we figured out where they were. Okay, and then once we do that, we're going to loop through every single pixel except for the very last one, and we should expect to see all ones, right? So so what that's going to look like is for bi equals, that's going to be byte index equals 0, bi less than or equal to, remember the last pixel, so 512 minus 1 minus 1, minus 1 times 4. Hold on. Let's just name this really quick. Int32 bi. This is byte index. I32 max byte index. So MBI equals 512 minus 1 minus 1. So this is the last pixel. This is the one before the last. Actually, no, what we could do, int32 max pixel index, MPI, max pixel index. So max pixel index is going to equal not the last one before skip bottom right. Did I say bottom left earlier? It was bottom right. Everything but the bottom right pixel. Yep, okay. Everything but the bottom right. Yes, it's the bottom right pixel in the bottom corner, like over here. Skip the bottom right. So that's why there's a -1, -1. That is intentional. Yes. -1 twice. That's not a mistake. I just want to make absolutely sure that doesn't look like it's a mistake. Then the maximum byte index, so this maximum byte index is going to be equal to the max pixel index times 4, and that gives us the component index of the red channel, and we say +0 red byte of last valid pixel of MPI pixel, right? Max pixel index, so it's the max pixel index pixel, right? So what we're gonna do is say, yeah, +0, +1, green, blue, alpha, right? And these are cumulative, right? So we're actually going to do 0, because there's no offset, add 1, 2, 3, right, to get the other things. So red, green, blue, and then this is alpha. And we are going to write it in this kind of like insane kind of way, just so that we can absolutely have a good visual and understanding of what's going on here. Red byte. No offset. I want to make it a little bit different than these ones, because I want to make certain that there's a reason this one's 0 and these ones are 1, right? So make it a little bit different. And then this is the byte of MPI pixel, so we can kind of, the top one is also, this is also a byte of the MPI pixel, but the most important thing to notice is that there's no offset for this first one, so that's kind of why I labeled it that way. Okay, so yeah, MPI times 4. 4 equals RGBA. Alright, so we can make a little inlined note there that, why is it 4? And it's because there's RGBA, and this is the pixel index. There's 4 bytes per pixel. Okay, so now that we have the max byte index, we can do byte index less than or equal to max byte index, and then MBI ++. And armed with that, here's what we're expecting. We're expecting that every single byte we look at is equal to 0xFF. So, we're going to actually dig into the actual data. So if we look at pixname, and we look at its data, this is the data for PAINT5D. So we'll say U08 pixel component byte, right? That's a pixel component. So pixel component equals this thing with the byte index, right? That is a bit long and convoluted, but it's very important that we know what we're doing there. And if PC is not equal to, or actually 0xFF, so a filled byte is not equal to PC, then error, your pigeon has a problem. Because we're doing a pigeonhole, basically, right? Like, If we're setting exactly one value for every single tile in the loops in the loop above, or hold on. Loop through set all ones. Oh, so we actually have to do that. So this offset dex right here, or actually not the offset dex, but the value is going to be 3. And this is binary 1 1, right? So that's why we're doing that there. And we can keep this, yeah, we can keep all that. And we're looping through, okay, so we have these 3 things here. Okay, that's good. And then we gotta loop through everything again. Once we're done looping through X and Y, we wanna make sure that everything is equal to this byte value. So yeah, this is our pigeonhole. Language. Your pigeon has a problem. Okay, now we want to take all this code and kind of copy paste. Okay. All ones and all zeros test bars. I'll just kind of declare them here. They're used in both of the loops below, so we need a common section to declare these, I think. So we'll just throw it in here. And the new variables we need to introduce are these guys here. So let's kind of throw these in here. So the byte index, the max pixel index, and the max byte index. We need to introduce all of those. They can be int32s, that's fine. We'll hardcode this put here. That's good. This U08 pixel component, whatever the heck, that's also going to be over here. Make a division here so we can tell the difference U08s, U32s, make a visual gap between those. Yeah, so we're just going to fetch this using the byte index. Also, before we accidentally segfault, assert that the byte index is less than or equal to 512 minus 1 times 4. Oh god, no, it's not that easy. So it's like 5... So this is the last pixel. And... okay, you know what we'll do? We'll take the byte index and assert byte index divided by 4. Right, because we're going through 4 bytes per pixel. So let's divide by 4 and then say this is less than or equal to 512 times 512 times 4. And so that's the... hold on. Byte index divided by 4, so now we're working in terms of pixels. So 512 minus 1. God, this is ridiculous, but yeah, that makes sense. make sure byte index does not cause a seg fault by going out of bounds. Right, so really we want the byte index should actually be less, a little bit less than this, like 4 bytes less than this. But that should be good enough because we have this max byte index here and we already calculated it. Yeah, that should be good enough. Then the pixel component is just a byte using the byte index from the CPU pixels for the PAINT5D system. And we're going to make sure that it's just equal to 0xFFF, and if it's not, the pigeon has a problem. Okay, cool. So why is our code kind of indented strangely like that? I think that we just kind of made a mistake. I think that's the way it... Ooh, that's horrible. Hold on. Okay, there we go. I think we just kind of made a mistake there. That's fine. So now we can kind of cut and paste like all this code and just change a few things, which is kind of like wasteful, but it is test code. So test code can kind of be redundant, right? Because it makes it a little bit more resilient to mistakes. And like if there's a mistake in one of these pieces of code, we can check the other to see if we think we like accidentally deleted something, backspaced on something. By having all this redundancy here, it will actually help us find something really stupid and horrible like that. So I'm not really feeling bad about having all this redundancy, especially because it is test code. It can be redundant, that's fine. Dead simple, right? It can be very dead simple. So everything needs to be a 0-bit, so instead of this here, we're just going to change that to that, right? That's all we got to do, right? And now, it's the exact same code. So set all... code I just want to make a note that this is the delta in this code block. Like, everything else is the same except for the 0 there, right? And, actually, no. There's another delta here, right? So, and the delta here is the 0xFF. Because now this is going to be 0, 0, right? So 0x, 0, 0 is 0 for 0. So let's kind of take that and go to the other piece of code where right, it's completely duplicated. Let's go over here, let's paste this here. And this is, the delta here is, right, this is 3. That's the different part. It's kind of hackish, right? We're just saying, hey, these things match. Sure, delta 3. It's kind of hacky, but, so then over here, Okay, so we could take this 0xFF right there as a delta, because right here we have 0x00. So 0x00 is delta of this, right? So delta. Right, so now we can highlight delta, and we can see the 2 points where these cut and pasted code blocks kind of change, right? So we got a lot of cut paste code. It's kind of ugly, but it is test code, so that's kind of to be expected, where things just kind of get out of hand and cut and paste all over the place. So if these tests pass, then I'm pretty confident that everything is working. So let's make an explanation of what's going on here. And that's not the video ID, is it? We're kind of tired, aren't we? It is 0077, and the time is that. The last 2 loops are so we got a nice little commentary here. We're going to have to change the timestamp on this, because it obviously took us a while to write this. A few minutes, actually. So we'll do 17 minutes and maybe 40 seconds. I don't know. 17 minutes. And how about 35 seconds? Okay, cool. 5 hours, 17 minutes, 35 seconds. Video ID 77. We're explaining the all ones and zeros test vars, and explaining what we're about to test beneath here. So the last 2 loops are pigeonhole smoke tests. And what do we mean by that? So we have a 0-0 binary test, And then we have a 1-1 binary test. So if we set the binary tile values, on that should probably be as. If we set the binary tile value as 0, 0 on every tile, we expect the underlying memory to be then. Okay, I'm changing the verbiage here. So I'm probably gonna have to change the timestamp again. I just looked at as I'm reading this, I'm like, the English sucks here. So we're gonna take this, we're gonna paste it here again. If we set the binary tile value as 1, 1 on every tile, and we can put some dots in there, some ellipsis, then we expect the underlying memory to be all 1s, except for the last 4 bytes. P5D binary test 1, 1. Okay, cool. So we got these little hashtags to identify the sections. And then we're going to stamp these onto what we're looking at. So all 1s, hashtag 1, 1, right? Bam, bam. And also we need to kind of... Okay, this is the 1, 1 test, right? All 1 bits. So this is the binary 1, 1. And we're going to do the exact same loop structure. And this is going to be our binary 0, 0 test. Okay, so there we go. So we got this. If we highlight these, we should be able to see them both highlighted, different colors, in our comment up here. Cool, so why everything but last 4 bytes? Last pixel cannot encode 3 layers, and thus is not used in the data structure to encode tile values. The last pixel of the quark map/mipmap structure is used as a special settings preset number pixel. Sounds good to me. Let's change the number now. So now it's 5 hours, 21 minutes. And, let's say 12 seconds. Okay, cool. So let's go over this. So all 1s and 0s test var. So these are the variables for the last test of the put get test of PAINT5D. And we have 2 binary tests. We have binary test 0, 0 and binary test 1, 1. And the comment is, the last 2 loops are pigeonhole smoke tests. If we set the binary tile value as 0, 0 on every tile, then we expect the underlying memory to be all 0s except for last 4 bytes. If we set the binary tile value as 1, 1 on every tile, then we expect the underlying memory to be all 1s except the last 4 bytes. So all 0s versus all 1s. Why everything but the last 4 bytes? Let me say that again. Why everything but the last 4 bytes? I injected a the that was not there. I do that a lot. The last pixel cannot encode 3 layers and thus is not used in the data structure to encode tile values. The last pixel of the quark map/mipmap structure is used as a special setting/preset number pixel. Okay, that sounds good to me. So yeah, what we're just going to do here is we're going to loop through px and py. So every single pixel of the buffer here, this buffer memory that we're using to store PAINT5D's tile map data. And we're immediately going to convert that global xy to the paint pixel variables, these things here. We're then going to use those paint pixel variables, so let's just make sure that they're all accounted for. So we're going to then use these paint pixel variables to set this binary value. But we're also going to have to loop through every single offset, so there's 15 of them, 0 to 15, because remember that we're kind of bit packing a pattern into every single pixel. So this navigates where inside the pixel we're bit packing. And we're going to set the binary pattern 1, 1 here, right? So this is our all ones test. So we can see P5D binary test 1, 1, P5D for PAINT5D. Okay, so the maximum pixel index is 512 minus 1 minus 1, because we do not want to look at the bottom right-hand corner. That's why we're skipping it. So the maximum byte index is the maximum pixel index times 4. But remember, that gives us the red byte. We actually want to go all the way to the last byte of that pixel. So we're going to add 0 to get to red, add 1 to get to green, add 1 to get to blue, add 1 to get to alpha. Right? Because these are cumulative additions. That's why it's not 0, 1, 2, 3 like you might be used to seeing. Then we're going to loop through the byte index all the way to the maximum byte index. We're going to do a little assert to make sure that byte index is not out of bounds so that we don't seg fault. So that if our byte index calculation, if our max byte index calculation is wrong somehow, we're going to crash here rather than seg fault when we look this up and end up out of bounds for some reason. This is the pixel component, R, G, B, or A. And we're going to say that value needs to be equal to 0xFF, which is all ones set within that byte. And if it's not, then the pigeon has a problem, and it's the ones test. Okay, so it's the exact same code for the zeros test. The only difference is where we've marked things as a delta. So we're going to go through every single pixel and extract the local tile values, or the local coordinates, right? So this is the global coordinate of the pixel, and these are all the different local values we need to identify this px, py, right? So it's a different form, right? And this local information is much more useful when in terms of the editor and your brush. So we're going to hit every single xy, convert it into these local coordinates, then use these local coordinates in the put command. But we're going to put a binary 0, 0 this time, so this 0. And also notice that, right, so we have to, when we put a binary 0, 0, there are 32 bits in a pixel, and we're only setting 2 things here. So if we have 2 things here, and there's 0 to 15 things here, so there's 16 offsets, 2 bits here, so 2 times 16, that's 32. So all the bits of the pixel are accounted for once we loop through every single offset here. So we have to loop through every single pixel, and also loop through every single pair of bits within that pixel. Okay, we're going to set them all to 0. Same calculation as before, the maximum pixel index, the maximum byte index, loop through every single byte, make sure we don't get a seg fault. The seg fault would happen here, so we're going to try to catch it here first. If we accidentally go out of the bounds we should be in. This is the pixel component by looking up the byte index within our array of pixels. And this time, every pixel component should be all zeros. And if this is a problem, if this does not check out, then we're going to say pigeon has a problem and 0 for 0. So if that all works out, then we're satisfied that the put get test kind of has passed, and we're just satisfied, right? We've done everything, and I'm pretty sure that we have now written all of the test code that we need. Now, we do need to add more test cases once we can get this running, but as far as adding more code, I think we're done. I'm hoping we're done adding code, because we've added so much code. I'm just hoping that what we've done so far, overflow, blah, blah, blah. Okay, so I'm hoping that the rest of this is just looking for syntax errors, and then we're going to eventually get this running again after a few days of not running. And is this in PAINT5D? is... Okay, so what's going on here? So this is unit test code, and it's this function min with int16, and so int16 is signed, so that's probably why it's giving me a problem, because we got this 0xff, and that's a little bit too high, isn't it? Implicit constant conversion. Yeah, because this is out of bounds. Right, because this function is taking two int16s. So to make sure this is not out of bounds, we can do the min between this and f, like that. I think that'll fix our problem. We're just a little bit too high, right? Because it's a signed value, so that means that we can't use every single bit. Implicit constant conversion. Okay, now what the hell are you talking about? Now I'm just kind of like, what? So let's look at this and be like, why is that? Because I thought int16 and int16, yeah? Okay. So I am not sure. I'm guessing that maybe these are naturally unsigned values if they're hexadecimal. That's my guess. But I don't know for sure. But here's the thing. I see implicit constant conversion. I see it's happening here. I don't see it happening over here. So, is this outside of the max value that I can use? Is that like a... maybe that's still outside of the bounds, right? So maybe that's still too high to decimal. So let's convert that to decimal really quick and see... is that outside of the range of int16? So 6, 1... oh, yeah, that is, actually. So if we look at it, int16... really? int16 max value. And trying to get me here. Let's go and Google search. 32,000. 61,000, yeah, we're out of our range here. I thought if I just kind of -1 that it would be good, but I guess we're going to have to do, like, instead of EFFF, we're going to have to go back one more. So A, B, C, D, E. So DFFF. Let's try that. Okay, so 57,000. And is that, really? Hold on. What the hell? Do I just not know how to math here? So int16 is 16 bits. It's 2 bytes. So, what's a U16? U16 max value. Which, it should be double, right? So, 65,000, yeah. 32,000 versus 65,000. That is what I expected. That's what I expected there. But what I'm really confused is that, well, I guess when we... oh, you know what it is? It's, I'm confusing removing a bit with just decrementing things. So, okay, I see what I did here. So let's do AFF and see when can we get like 32. How about 9? So we need it to be less than 32,000. I don't know my hexadecimal that well, so we're just gonna keep on going down until that is less than 32,000. What about 5 FFF? That's a little bit too low for my taste. Let's, 28,000. How about 7? 32767. Ooh, 32767. Okay, so that is the max value of that number. This number actually looks quite familiar. So, okay, so over here, this is actually what we need if we're going to, yeah, if we're gonna do this. Okay, cool. So now we're hoping to avoid that implicit conversion because it's not outside of the range. Large integer implicitly truncated. Okay, so we're actually in another function now, though. So we fixed that. Yeah, so that's what I thought. We're in here now. And 51,000. Yeah, I thought, did I say 51,000? Why do I keep on doing that? 5,000, jeez. I just, my ego is like, haha, yeah, I wrote a lot of code. Not that much code. Did not write that much code. So, why is this... Is this just a trap value? So the max... cap min, cap max, this function, this UX thing, and then assert that it's equal to this. Oh, I see, okay, I see what we did. So we're trying to say, oh, between this, lower boundary, upper boundary, the problem being that our boundaries are out of bounds. They can't actually be expressed in... Right, this is the highest thing we can have. So this maximum boundary, this is as high as we can go. Ooh. We have extra zeros, don't we? Okay, hold on. So let's undo that. So our logic here might actually be correct. It's just that right, so this F is somewhere in between. This F's on this side, this F's on that side. So that should actually work. And then this hard-coded thing, do we have anything else hard-coded? Nope. So this F is the min, right? And... oh, this is not the min. This is the bruh, right? Bruh between the min and the max. And it's initialized in the middle. So we're expecting to have the unchanged value, have that same value there. Okay, that's fine. And then some other values that aren't hexadecimal that we're testing with. So just whatever, we don't care. And int32 cap u32. So, oh, this is an int16, int16. So, there's weirdness going on with this function. This function has a weird signature because it's tailored to this piece of code. So the cap function is tailored for PAINT5D's usage. So it's an int32 that's being capped by two u16s, right? So min and max. But this is an int32 here being capped by two unsigned 16 bits. And then it's returning an unsigned 32-bit. Right, that's weird, but that's but I only use this cap function in one place, so I could afford to tailor it exactly to the needs I had, and that's why it's like that. Okay, and then function is this thing, and yeah, that's good. Okay, let's give this another run. I think that we fixed the overflows that we did in there. Reaches end of non-void function. So this is paint5d.f. Interesting. So 437. I don't know how we're all the way over here and then all of a sudden it's like back up here. How does that happen? I don't know. I was expecting it never to come back here. I don't know if it like does things in multiple passes. Okay, so 437. Non-void function. It's UO8. Do I actually need to use this? Paint5D diagpics converted to ASCIIpics. Ooh, hold on, there's a big comment here. Diagpics has a no op on it. Some timestamps. Cannot make this function because blah blah blah, because blah blah blah, information loss, fine. Okay, I get it. So we can't make this. So, well, if that's the case, then I get why we have a UO8, because if we actually had this function, it would be returning some type of 8-bit value. But even though we're kind of going to immediately throw an error in here and say you can't do this, we still need to stub it in properly so that the code compiles. Non-void function. Is it another function that we cannot make? EO8. Diag picks. Oh, hold on. Oh no, now we're at like 2000 and what the heck. So, let's go G. I don't know how that happened. So 2, 3, 5, 6. Okay, so what is... So this is a non-void function right here. So this is a private unit test. Is it being called from anywhere, or is this just the way... No, it's not. Reserved for future use, blah, blah, blah. Call all the stuff, system data restore. And then let's just return 0x00, right? Because that's what we've been doing for everything, where that expects some type of bit mask value, but we're not actually implementing it yet. Or if ever... Sorry, we might never implement this. But it's there if we want to. And we have to keep on doing that for consistency with all the other functions we wrote. So U1 is uninitialized in this function. So tau depot put, and we're in 13,000. Like, why is it all of a sudden kind of like going all over the place? And I don't know, and it's kind of annoying. So if we look at, why do I keep on saying, I keep on saying one more order of magnitude than it really is. 1,300, probably because that's harder to say than something thousand. 1,300, right? 1,324. Okay. U1 is uninitialized in this function. That's probably true, because it's unused value. But I guess, even though it's unused, we still have to set it. Okay, that's fine. Let's set it to a value that's most likely to memory stomp. And you know what that is? All the bits set. R, G, B, and A. So we can make a note of that. Set unused values 1, 2, 3 to all 1 bits so that they ensure a memory stomp if our code makes a mistake. Okay. So right there is a reason that we're going to use this, right? There's a reason that it's going to be that pattern. And we can also do, you know, at vid IID 0077, and the time is 5 hours, 41 minutes, and just 42 minutes and 0 seconds. How about that? Yeah? We've been waiting for this moment. Yeah, so set unused values 1, 2, and 3, U1, U2, and U3, to all 1 bits so that they ensure a memory stomp if our code makes a mistake as to where to put the bits. And what I mean by a memory stomp is overwriting a memory address that we should not be overwriting. Now, we could say that instead of doing a memory stomp of all 1s, maybe it would make more sense to do a memory stomp of all 0s, but usually cal-oct memory is less problematic than having 1 bits where they shouldn't be. So I feel like this is the most devastating pattern we can use to ensure we find mistakes. If that makes sense. I don't know if that makes sense. Whatever. Well, let's just section this off, and we're done explaining it. I know what I mean. We got a commentary. We got some video recordings. Ask me about it, man. Email me. I'll give you an answer. Unless I become, like, super famous and can't answer my email, then maybe I won't, but, I'm not super famous now, so email me when you can. Okay, so that looks good. Let's give this another run and see where we end up next. I'm gonna guess we're gonna end up in another function just like this, because this is probably cut and paste. Yeah, like this looks probably identical to this, right? Yeah. Okay, anyways. MI is used uninitialized. Okay. 2482. Or maybe not. Oh, because we actually did use... Okay. 2482. So now we're keep on bouncing back. Okay, so this is infuriating. So I would expect the errors to not be like bouncing around like this. Okay, so 2482 TI, and then there's this MI, and so we're saying that MI is not initialized. And is MI anywhere? So there's MI, max index, max test index. Okay, and the maximum test index is just the number of tests, right? So we can actually take this and you know, MI, max test index. Yeah, so it's rows minus 1. So if we have, right, because 24 plus 1, because the index plus 1, but now we have to minus 1 to get back to the index. And 0 to 24. Yeah, so 24 plus 1, and then minus 1, we're back at 24. This is the last index, max index. That looks correct. Okay, cool. Are we just going to be doing this all day? Okay, so I'm going to guess we have some cut and paste code, and if we look at the next function, we're going to find an uninitialized TI, or MI. So if we highlight this, I'm going to guess we did not set this. So MI is probably declared right here, but it's not set, and we know that we just need rows minus 1 to get the maximum index here. So in here, we're just going to say, you know, MI equals, you know, rows minus 1. And then we can say, you know, max test index. Okay, let's keep going. Test index times the stride. Columns, number of columns. Yeah, that's the stride. Okay. Ooh, hey, look at that. We're compiling again. Okay, so let's see what crashes. Because I am certain that... What the f... Oh, you know what? So we're probably not running our test code yet. And even if that's the case, our keyboard doesn't work. Oh, hold on here. So something bad is going on here. So I think that first of all, is this test code being called? I don't think it is, first of all. Because we have some other type of problem. But I don't think this is being called because I would expect something to crash. But we're compiling, so that's good. So let's look at section unit test. I think it's called section unit test. You know what we're going to do? So it's called unit test section. I would rather not have to think about that. It's also a huge section. So we might as well... It's a huge section. We might as well double label it, right? It's like this huge section. So let's kind of say, you know, okay, this is in the middle. So, section unit test. Alright, we'll just relabel it like that, so we don't have to think about which thing we called it when we want to find this unit test code. We can just be like, bam, there it is. I don't think this is being called from anywhere. Otherwise, I'm sure that it would have failed us. And yeah, so I don't see this unit test being called from anywhere. Let's actually match the whole word. So there's only, yeah, it's only here. It's not, yeah, it's not being called. But we still have, like, another problem, which is, like, the keyboard listener all of a sudden is bugging out, where it's like, oh, you know what, no, actually, my bad. So I think something performance-wise horrible is happening, but it is most likely this. Suspend the hotkeys. Okay, that's good. Okay, whew, okay, I was scared that we introduced some type of horrible performance problem. No, it's just that, my hotkeys do not like the, my hotkeys never interact nicely with any type of keyboard listener, even the stuff I've coded. So, it's because I think they kind of, intercept key presses or something. I don't know, it's weird, because it's like, it specifically doesn't work with games. Because it works fine with, like, I can do my key presses for, like, typing and whatnot, but, should probably figure out a way to fix that. I'm guessing what happens is, I don't know why it works with... It has something to do with the fact that you can't, like, hold... So, here. Well, let's show you. If we go into a text editor, and, like, open up a new thing, and without our keyboard shortcuts, if we just hold a key, we can go like that, right? We can kind of go like that. Now, if we do not have... If we unsuspend our hotkeys, right, so that we can have shortcuts, then if we hold down the key... Actually, that works a lot smoother than I thought it would. You're just gonna have to trust me that holding down the key is not as smooth when the shortcut script is enabled. So yeah, we'll suspend those hotkeys again. I don't know how to fix that, but what we do need to do is we need to get this unit test code running. So how do we get the other unit test code running? Do we just have like a I'm gonna take a wild guess and say that we had some type of wild guess says we had some type of lazy call to some of these functions. Like some of these functions check to see if the unit tests were invoked and then ran them. I think that's probably a bad idea. So how are we gonna fix that though? We're gonna have to, until we get all of our unit tests working, to avoid a lazy solution to unit testing, Yeah, so let's think about it. So we have unit tests for basically everything. So if we look at, well, actually that's a lie. We don't have unit tests for everything. But if we look at like tau rec, right? We did tau rec a while ago, or recently, I should say. So tau rec. Oh, not tau rec, but tau type. And if we look at that unit test, oh, we call it in the init none. It's actually not, that's not a bad idea, right? Because it's, god damn it. Yeah, so in init none or the initializer, we're calling the unit test. So actually, you know what? I'm okay with that. I am okay with that kind of pattern for doing it. Because then the tests are only called once, because those initializers are only called once. That might not always be true, but mostly it's true. And yeah, let's so let's do that. So this PAINT5D function, we're gonna make a public version. So U32. So if we do U32 of this, takes the U32 called U32. And this is just kind of syntactic bloat to adhere by the conventions I use. But we're going to make this a private function. And it's just going to forward declare this thing. And we're just going to do ext avod, that thingy takes vod, right? Vod being void. And it looks like we have enough room to where we don't really have to write it in this terse way. And also, that's not void. It's extern, takes a U32. There's a U32 here. Let's actually give it the U32. So this is the type, this is the actual variable, right? So those cases are intentionally different. We have enough room where we can just say extern. We don't have to do ext. If we have enough room to actually say it, then we're going to say the whole thing. So this public, all it's going to do is call the private, right? And we should probably have a guard against initialization of this multiple times, because I'm thinking that the PAINT5D system may... yeah, we gotta match the whole word here. The PAINT5D system, I'm thinking there could be the possibility that it's going to be initialized more than once. So if we're calling the test function inside the initializer, we're going to have to think about that. So let's look at PAINT5D init, right? We're expecting that to be a thing, either init or init none. Looks like there's no init. Oh, match case. I don't know what I did there. Okay, so PAINT5D init. Okay, PAINT5D init. And I hope I don't have corona, because I feel like I have a cold. Yeah, no more eating out. It's gonna get me sick. I don't go out to restaurants, but, like, getting takeout, still, that could get contaminated. And my food was put together half-assed. So, yeah. Fuck. Okay, so PAINT5, great, now I'm worried. I don't need more health problems. Okay, PAINT5D init. Now I'm worried, and now I can't think. reserved for future use, init call count, plus plus, current editor, likely unintentional recursion. So if, okay, so just making note of the editor that's being initialized. And okay, so all this stuff is good. Do we have a private PAINT5D init, or is this it? This might be it. Yeah, that's it. Okay, so, you know what we're gonna do? We're just going to... run unit test if never ran before. So right here, we're going to run the unit test if never ran before. Right? Keep it kind of simple. We're just going to hide it down in here, right? So it's kind of hard to untie the unit tests from your code when they're kind of buried in there, which I'm okay with. So here's our unit test. And if we look at the PAINT5D data, what kind of data do we have here? We have a lot of stuff. What do we have? Debug variables, init call count. Technically, I guess, if you want to think about it, a unit test ran is kind of a debug variable, right? Because unit tests are basically debug, if you think about it. So, we'll just say, you know, AAC 2020, PAINT5D unit test Okay, so it ran or running, right? So either one of these cases, we're going to run this, okay? And ran or running, so it's kind of improper to put it here. But if this is the only place we're using it, then it's fine. It makes the code readable. So we'll cheat like that. Ran or running, less than or equal to 0, and now it equals 1. And once we're in here, we'll call it, right? So it's only going to get called once, because once we get into this block, we're going to set this to 1, so it'll never be it will never be used again. And yeah, so now we're going to expect the code to crash on some type of unit test somewhere. Or that. So define UO8. So let's make sure I can taste things. Okay, well, coffee's still bitter as fuck, so that's good. It doesn't worry if you... Yeah. Let's give this a run. We need a for declaration for this. Extern U32. Taking a U32. Right, we don't use for declarations except for in these cases. In the case of I don't know why I did 0x. Oh, 0x00. Oh, because it's 1 byte. That's why we did 2 x's, even though it's a U32, so it's like 4 bytes. Whatever. That's the way we've been writing it, so we'll keep on writing it this way rather than this way, right? Okay, let's give that a run. And once we crash on the first unit test, we're going to, I don't know, think about how much we hate ourselves for what we've done, and then, I don't know, go to bed. 2291. Control reaches end of a non-void function. It's like, why now? Why now? Tell me about that. I don't care what the return value is. And also, oh, this value does get used, so that's okay. Okay, here we go. Moment of truth. See what crashes. Ooh, boy, okay. So, fatal, actual diag not equal to expected diag. Ooh, boy, we're gonna have tons of fun here. Okay, so, diagonal test, yeah, we're gonna have problems all over the place. But we're through one milestone where we got compiling again. So that's good. So we're at a safe point where we were kind of worried that we added so much code we wouldn't be able to compile again. But no, we're compiling again, and before we ran the unit test code, everything was behaving properly. All the previous systems seemed to be doing what they should have been doing. So what we have to do now is we have to just go through all these different tests we wrote and fix them, right? Find all the problems and fix them. And there's going to be a lot. So I'm going to tackle them as they happen. And so the problem now is that we're going to have to look at the errors, and then we're going to have to look at the tests, but we didn't write the tests in the same day, so we're going to have to, like, wrap our mind around the stuff, you know? So 6 hours is actually 30 more push-ups and whatnot, I think. Let's see this. Push-ups. 40. If we do 30, we're at 70. I go to bed, though. Yeah, let's just commit this. Let's commit this, because we're at a good point here where, so it's not completely broken. So, git status, git add dot, git commit dash am, semi-broken, unit tests failing. So it's semi-broken because when I say broken commit, I usually mean that it does not compile. It compiles, but the tests are broken. But it's still it's not release worthy, so we're just gonna push it to the private GitHub, and we're only gonna post to Kanji Coder once it's no longer broken. So. Okay. So I'm going to take a break. It's been 6 hours. I want a break. Maybe I'll come back. Maybe I won't. I don't know. Yeah, this has been part 10 of PAINT5D. Let's, yeah, I'm going to get out of here for now. Or actually, I probably should do my 30 extra push-ups and everything. But I also said that if I did that, I would go out on the trampoline and jump. But if we don't do it, then when are we going to do it? And I don't like how pudgy I am getting, so I should probably do it. So let's do some push-ups and hope that we're not dying of coronavirus. Fuck. Okay, so push-ups. We're getting a timer for how long this takes. Last time it only took us 5 minutes to... is it? Okay, this is not right. Oh, because it's not, this is not the, this is the split timer, isn't it? Yes, it's a split timer. Push-ups, and it's not red timer. Let me rename this. Hold on. Okay, so this is the, that's a split timer. It's not the countdown timer. That's why it didn't fit. Okay, let's just do this. Get it over with. As long as I'm not dying, then I'll be happy. Okay. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, okay? Crunches. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. Squats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, dumbbells. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. Okay, so we're gonna go out, jump on the trampoline, and be back. Okay, so 30 jumps on the trampoline and all of our push-ups and stuff. Only 7 minutes. And we are done for today, I think. Or maybe not done for today, but done for this video. And maybe we'll be back later, I don't know.